product development, and advanced hardware design. He has also contributed to research oriented engineering roles in India, further strengthening his expertise across electronics and embedded technologies. Currently, Vivek sir is an electronics application engineer at CATFEM India, where he collaborates with leading organizations in aerospace, telecom, automotive, and defense sector. His focus area include antenna design, RF design, IC packaging, PCB development, signal and power integrity, and EMI EMC compliance. In addition to technical consulting, he actively delivers training and workshops, empowering engineers to adopt cutting-edge simulation methodologies. With his blend of international R&D experience, practical engineering skills, and customer-focused application expertise, Vivek sir brings a strategic perspective to solve complex challenges in modern electronics and communication systems. We are excited to welcome him and look forward to benefiting from his insights and expertise. Sir, I humbly invite you to address the participants.
Yeah. Hi, thank you. So, good afternoon, everyone.
Good
Thank you so
afternoon, sir.
much. Thank you so much for this warm introduction and warm welcome. Thank you, Prachiman. Thank you, Mohit sir.
Thank you, sir.
So, can I start, Mohit sir?
Yes, sir.
Yeah. Okay, great. Thank you, sir. So, just allow me to share my screen. Okay. I hope my screen is visible to you.
Yes, sir, it's visible.
Okay, so I'm on the first slide of my presentation. It says that 5G antenna design. So just to confirm, actually I have two
Yes, sir.
screens, so to confirm.
It is visible.
Yeah, great. Okay, so once again, good afternoon, everybody. I am Vivek Prakash Yadav. I'm application engineer in CATFEM India Private Limited. I do take care of high frequency applications, which contains like tools, HFSS, SI wave, and the applications where I work mainly on in antennas and in terms of if you say PCBs or RF, signal integrity and power integrity. And then I do work professionally with one of my executive professors for antennas and the AI based and ML based antennas. So these are all where I work in now. And today we are going to talk about 5G antenna design and simulation from concept to installation. And this is the one concept like how we can go with, well, like, okay, let's say you're starting with a design, with a concept, and until this installation, until the finished product you are going to get. And so what is the process and how you can simulate all those things, how you can do analysis before doing a project. Okay, so we'll explain that one. Okay, then thereafter how we can do meta surface and MIMO antennas, what are the different toolkits in ANSYS mainly. Okay, so that's all we are going to talk about today. Okay, and so this is the agenda. We will be here like about us, about my CATFAM where I work. Okay, where from where I was approached here. Okay, so and then what is ANSYS electronics product portfolio? Mainly why I'm explaining this product portfolio, because we are going to use this tool. Okay, and I'll explain you how you can use it in different applications. Okay, then what is the background of 5G? A bit I'll give you, but of you are the industry, like academic expert, better than me, better understanding for 5G and the different bands there. Okay, then how you can design an installation like from in a 5G or 6G, whatever the application you are going to talk about here. Okay, and then practical examples like, okay, some 5G antenna. I'll show you how you can design it practically. Okay, some how you can create an array. Like let's suppose you are talking about the 5G and all. You need to think about the arrays of antennas. Then meta service as same. So I'll show you one example and one both 2 3 examples on this. Okay, and then how the different toolkits are there. One toolkit is MIMO toolkit, and then other different tools that we are included in ANSYS HFSS. So how the different tool can be helpful, where it could be helpful, okay, and where you will find all those things. So this presentation all is going to help you how to design your uh, your what is it, whatever you're thinking in the terms of 5G or 6G. Okay, and what tools can be helpful there and different steps. Okay, so yeah, let's start. Okay, so if I talk about the CADFAM, CADFAM is a group that started in Germany. It's a German-based company. We are a multinational company, we can say that. Okay, so and we have a like number of expertise, like 450 employees are there all over world. It number could be changed here a bit, but thereafter, if you talk about we have the different we are at the different locations. Okay, 19 plus companies are there, and let's say 35 locations, 30 countries. Okay, so these are the one overview of a CADFAM group. And let's say if I talk about CADFAM India, so uh, we started in 2007. The headquarters is like in Hyderabad. Okay, and we have a different offices in like Bangalore, Pune, Gurugram, Chennai, Coimbatore, and Ahmedabad. Okay, so and we do services, we do what do you say, technical like supports and trainings. We do provide all the services here. Okay, so this is all about CADFAM. Okay, and so as I was talking about ANSYS electronics product portfolio. Okay, and in that, I mean, if we talk about the electronics one, we have ANSYS HFSS that is called general purpose high frequency 3D electromagnetic solver. Okay, so mainly we say it, general purpose and arbitrary also. So it means that you can model anything, you can simulate anything here. So it's not specific to any any kind of specific geometry. So you have to put a specific geometry, then you can simulate it. So it's arbitrary. You can model anything, you can simulate anything. You just need to know the basics. Okay. Thereafter, we have ANSYS Maxwell. In that, you can do low frequency simulations. It's also arbitrary too. But the low frequency means application wise, if I say like electrical motors, machines, actuators, and such, this type of simulations you can do it. ANSYS Maxwell. Thereafter, ANSYS Q3D and 2D extractor. That's for extracting RLGC parameters. Let's suppose you're working on a RF circuit, and then there is a bus bar you're working like high power PCBs, and that we uses bus powers. So what we can do if you want to extract the RLGC parameter for that bus bar, okay, so you can use this tool to extract those parameters, and then further you can use it in any of the tool in ANSYS. Okay. Thereafter, we have SBR plus. Let's suppose you have an antenna, and I have a case on this, how we can use this one. Okay, so this is one type of solver, SBR plus solver, that you can see the performance, installed performance of an antenna. Let's suppose you have a big plane or a high mast, or maybe a tower, you can say that. And on that, you are installing an antenna. Okay, so how it's going to perform there? How it's going to interact with that metal, how the radiation pattern is going to change. So will talk about that in SBR plus, and I'll show you one example how we can how this is to be useful there. And Amit is one other tool in ANSYS electronic desktop that is called like let's suppose you want to do post-site simulation, interference, limit margin, kind of those things. You can do it in Amit. Okay. Thereafter, we have ANSYS circuit. So we can do layout designing, it's a schematic, RF, and this sort of mixed signal design analysis. Thereafter, we have ANSYS SIV for PCB based signal integrity, power integrity analysis. So if you have a PCB also in your design, so let's say you're talking about whole system, then you can use that one also. Okay. Thereafter, we have ISPEC. So for thermal analysis, I'll explain you how you is useful in an aspect there, like thermal analysis. Let's suppose if you design something, there is a EM loss there that can cause to a thermal issues also. So how you can do analysis of those things? We'll check this one. Okay. So this all are the like one short overview over the and this electronics portfolio. There's a number of tools in that also, but not useful here, so I'm not explaining. Okay. So yeah, let's say we talk about the the 5G background. What is the 5G? So mainly we are right now we are in 5G era. Everybody is working. Okay. So and then we come at like okay, what are the different bands there? We want to discuss that one. Then 5G is like okay, everybody wants to use it now. Every device wants to go on 5G. Let's say an IoT device or any kind of testing. Okay, so sort of analysis you can sort of tools required for 5G, and in that is increasing up to designing of another 5G antenna for each devices. Okay, so that's where we are booming in. Okay, 5G is 5G antenna development and all those things. So this is how you can use like there is a requirement in waves. There is required kind of a small cell. Massive MIMO is one concept there if you want to and then a beam forming. Okay, so how you can do a beam forming, I'll explain you those things. Okay, then full duplex communication we are looking there. So let's say you're talking about the AR or any applications, any sort of application that is connected right now. Okay, so everything is going to be shift on 5G because 6G is still in development phase, and 5G we are in the phase there. So if you were talking about any of sort of application, everybody wants to go on 5G. Okay, and this is one example like how number of antennas are there on your phone. So antenna, there's antenna like 8 or 9 antennas are there on the phone. Okay, patch P5 antennas, any kind of antenna you'll find there. Okay, so and let's say if you talk about the spectrum also, there is a one number of bands are there. Okay, in 5G there's a high bands that are referenced by Nokia. Okay, so you can show this bands are right. Okay, and then mid band as a there 3.5G, 6G, where 4G and 5G coexist there. And then if you talk about the mid band, 5G, 4G, 3G, 2G, everything is there. 5G mid band and low band. In high band, 24 to 40 gigahertz, we are only at the in 5G. And let's say if you talk about a 6G, we are from 100 gigahertz, we are talking about 100 gigahertz up to 1 terahertz. Okay, and that's all are doable. Whatever is antenna you're going to design in any of the tool. Let's say we are talking about the NCS here right now. So in that, it's also you can do analysis up to terahertz. Okay. Thereafter, this is the one pros like why we are talking about the 5G. What is the issue there? And when we are talking about the 5G, there's a number of antennas are increasing like day by day. There is number of like previously, if you talk about the 4G low bands or 5G bands, you can install one antenna and we can do cater a large number of area there. Okay, large number of devices there. But if you talk about 5G waves, we cannot cater large number of devices there. The reachability, is not there. So you have to install each like number of antenna at a particular distance every let's say 100 meter or 500. I'm just giving any example, rough example, but you have to install an antenna or 5G antenna, based antenna on a is particular distance. Okay, this why so if you go in a low band frequency, the wavelength is bigger. It can cross the buildings and it can go over the buildings there. Okay, but if you talk about MMUS, the wavelength is shorter. Okay, it cannot penetrate the buildings or anything. So you will not receive that that type of connectivity we are looking for. Interference is there. So this all parameters are going to interfere there, and that's why we are like the number of antennas is increasing day-to-day life. Okay, and then number of softwares also increasing to handle those things. Okay, thereafter also additionally, let's say we are talking about the AI and also here. So we want to optimize our radios. Okay, how it's going to interact, how it's going to connect with that device, how it's going to transfer all those things. Let's suppose from one ready to another system or another base station to another base station, how it's going to be. Okay, so this all can be doable there. Okay, how you can interact with the system. So this is all overview over the different 5G and mm antennas. Okay, so this, if you see here, like there are the pros and cons. You have read it, okay, already. But so there is a few requirements there, and there is few antenna designs. So these are the requirements for mmwave. Okay, link budget and should be high gain, high power we are looking for, and that's why we want to optimize it. So also I'll talk about how you can optimize your design. Okay, how you can use also AI and ML technique to optimize your design. Okay, so and then we'll proceed with like that. Okay, so if I say how we are going to design, let's say I was talking about concept installation. So this is the method we are going to talk here. Okay, from there is an introduction a bit on that. Okay, what is the different flow. Okay, then how you going to design an element design or maybe unit cell. Okay, so we will talk about that one. Okay, then that's like phase array analysis, installed performance of the antennas. Okay, and then link margin interference analysis, and then thereafter a multi-physics thing. Okay, so let's suppose you have an antenna. You are getting, of course there is a EM loss, so and also you're getting the thermal issues there. So how you can analysis this one, like thermal analysis of that particular product or particular antenna or array of antennas there. So all those things can be so such type of analysis, like thermal analysis, we can do in ANSYS iSpec, and it's two-way coupling is there, and HFSS and iSpec. So you can do both things there. And then obviously, let's say if you talk about the structural reliability of your system. Okay, so you can do also the structural reliability there. Okay, using ANSYS structures or structural and tools there. Okay, so all are these interlinked, and that is called multi-physics solution to any of the product that we have here. Okay, and then an automation workflow as how we can automate the workflow, antenna design and everything, and additionally how we can integrate the terms of AI and ML techniques there. Okay. Okay, so let's say here we want to go from like nanometer level to the kilometer level. Okay, and this all the simulations can be doable from, let's say, talking about the transistor, okay, up to the network planning and base coverage. So all this, whenever you think about that at each level, like PCB level, you want to do analysis, you can do it. Okay, analysis, okay, in terms of any optics, semiconductors, electromagnetics, structures, fluids, and then methods of, so all are there is a application that can help you in doing this such type of analysis from transistor level to the network planning level. Okay, so let's say we talk about the product development workflow. Okay, so let's say we start with the design and verification. We decide our requirement, what is the radiation pattern and all those things for an antenna. Okay, and then what tool we require here, if you see HFSS, 3D circuit, iSpec, and mechanical, all these tools can be needed to design and verify. And then there is Amit and SBR plus also for co-site and also install antenna performance there. Okay, and thereafter, once you get those things from this block, let's say you see a one block here. Okay, and then you can do you'll get a E field and S parameter. Thereafter, you can do the network planning and the condition that is fulfilled or not, according to your requirement. Okay, then let's suppose you're not finished and you say no, okay, you didn't receive that one, the whatever the requirement you're looking for. Okay, so what you can do, you can go back to this, like this system again, you do analysis again, and you can again come back. So this kind of analysis is doable in ANSYS. Okay, ANSYS HFSS and also other tools that is okay, more useful there. Okay, so these are one of the like design workflow for 5G phased array antennas. Okay, So firstly, what we are going to do, we are going to design. This is an initial step. Okay. So antenna array and antenna element and array design. So let's you first need to design an unit cell. Okay. So say if you are talking about the 5G, there is an array of antennas of course, you know. So be- because in 4G we are talking about a single antennas there. Let's say okay. But 5G, of course, you need an array of antennas. So to do that one, okay, you need an unit cell. Okay. And let's say also you are talking about a meta surface. If you want to create a meta surface, you need a unit cell there. Okay. To further, let's say you have an unit cell design. Okay. And then thereafter you are doing DOE, design of experiments there. Thereafter you're creating an like let's you design, you have a unit cell, you're doing experiment, you got some result, better results. Okay. And then you want to improvise the gain and all those parameters because in 5G we need that one. Okay. So it's how, and after that, once you have a unit cell, how we can create a array of an antenna. Okay. So this antennas, like let's say you want to create different methods to do in NC such a process, uh, such kind of antennas. Okay. Let's say, uh, okay. Thereafter, how you can create a different antennas there, like let's say 2D antennas, 3D antennas are there. Like what type of array you are looking for. Okay, how you want to explicitly copy paste in your design. Okay, we'll discuss those one. Okay, thereafter we have install antennas. How you want to see the performance of an antenna that is installed over an mast and over tower. You can say that. Okay, network tower. Okay, and or any, like let's suppose you design an antenna that's going to work on an aeroplane. Okay. So also you can place that antenna for whole plane in SBR plus soft because it's quick and easy to solve it. Okay. And then you can do this type of analysis like a stock performance antenna analysis. And then let's say you are talking about the systems. Okay. Like let's say you want to do link margin or interference analysis, coupling between two models. Okay. Uh, Also, the coverage and estimation, all those things can be doable in the combination of SBR plus and Emit. Okay. Thereafter, network planning and coverage, as we would explain you a bit. Okay. There is a MIMO antennas there, and then network planning like base station user, like handoff, coupling handoff, like between two base stations. How we can do that one. So let's say if I explain you something, if you have seen here this one, this example. Okay, there is a two base stations. Okay, and one thing, one moving car is there. So how the network coverage is, how the base handoff is going here. We can do such type of analysis in ANSYS SBR plus solver. Okay, and you can see this result. Okay, handoff between the cell towers. Okay, so this is one example here. Okay, so let's say and thereafter you want to do a multi-physics analysis. Okay, here you can do temperature analysis, like thermal analysis. You can do their structural reliability, and also they both are two-way coupling. Okay, what do you mean by two-way coupling? Let's suppose you have a EM loss. You want to do thermal analysis. You can push that EM loss to in ANSYS iSpec. Okay, and you got some thermal plot there. Okay, because of that EM loss. Okay, thereafter you are not satisfied with the result. You want to push that temperature loss in ANSYS HFSS again. So you can use that again to do further analysis on that until the you satisfy with your result, what you're going to get there. Okay. So yeah, that's all in this slide, I think. Yeah, yeah. Okay, so we how we can design an element unit cell. Okay, so this is one example of what you say cross dipole antenna is there. Okay, so what we are designing, we are using periodic boundary conditions. As if you talk about the arrays, you have to use the like boundary condition, periodic boundary conditions. Okay, and let's say if you're talking about metasurface antenna, you need there a flow keyboard. Okay, So you on top you are putting the okay port, and bottom if it's required, it's not required, you don't need to put it there. And then you have a one design, and then you are doing design of experiment. Like you are obtaining response. Okay, what should be the max as per one, max to one, or max two to two? What should be the cost? So this kind of this optimization is there. Okay, so this all this design of experiment is there. Once you have an unit cell, let's say you created one unit cell, you want to do optimize the design, and but further you want to play with the different aspects also. Let's suppose you want to play with the length, dipole length, or dipole width. You can define this type of experiments you are looking for. Okay, and then you will see, okay, what is the maximum cost, and cost you can define there also. So this kind of result and this analysis you can do in NCS HFS is using Optimetrics. Okay, and also there is a OptiSlang tool called to optimize your design using AI/ML techniques. There is already a lot of algorithms are there to optimize those things. Suppose if you have one, you can use one. You can include that one also. So let's say I want to design an antenna. I want to start with the basic thing. Okay. So this is one antenna toolkit in HFSS that can help you to get any unit cell for you directly, easy. Okay. So I'll explain you how you're going to get it, where you'll find it. Okay. And there's a number of antennas. Let's suppose one. I think you can say that 50 or 150 antennas are there. Okay. So you just click that one. You define your center frequency and all those things, and then you'll get a click on finish. You'll get a designed antenna. Okay. You have to do analysis. Okay, so this how this can be helpful there. Then you can define you have a basic design. Okay, and then there you can play with the dimension or anything you're looking for, and but you don't need to start with a sketch. Okay, so this is one tool that can be helpful to get an unit cell there. Okay. Okay, and how you're going to get the results? These are like gain, directivity, 3D we can beam if you're looking for. Then you want to find the polarization, is it a left-hand polarization, is it a right-hand polarization? Those type of analysis, input impedance if you want to see, return loss kind of thing. So this all can be analysis further, like these are the few plotted results. Okay, but if you want further analysis, you have expertise to understand the results. There's a number of results are there. Post-processing data are there. You can post-process them there. You can do, further get. You should understand. You can get the number of data there. What you're looking for. Okay. Thereafter, how we can going to create an array. There's a different methods. Okay. To create an array, there is a one explicit. Okay. What you can do, you can explicitly copy it. Okay. Let's say one block you are copying there. One unit cell, and then there's a one unit cell here, and you're copy pasting on each block there. Okay, so but this is one technique, and then there is a finite array technique, FADTM techniques we say it. Okay, and then there is a what do you say, CADTM technique, component array DTM technique. Okay, domain decomposition method. So we say it like that. Okay. But here we are going to talk about the different techniques, the arrays we are going to create here. I'm going to explain you how you can use what you see explicit also. Let's say I'm not going to show you, but it's just a copy paste. You can do it. I'll explain you can do that in a quick way. Thereafter, how we can use FADTM technique or CADTM technique to create an array of your antennas. Okay. Thereafter, let's say there is a different number of antennas. Conformal antennas are there, not conformal. So this all can be handled. You have to import your number of unit cells, okay, to create a particular design, and then you can do further level of the performance that you're looking for there. Okay. So let's say the next is thing. How you're going to create and what is the installed antenna performance there. Okay, so this is the one thing. Let's say you want to use you want to place that antenna, whatever you have developed. Okay, after the array of antennas, okay, you want to place it on a mast. and you want to see what is the performance of that antenna on particular place. Let's suppose you have a number of antennas there. Let's say this one is one antenna, this one is one antenna radio, or you can say that. Okay. But here, what we're going to use, let's say whole this mast is an what do you say, metal. You can say that. Okay. So we are placing the particular antenna that you have designed on this. Okay, and we for analysis using integral equation or SPR plus solver. Okay, you can use both method solvers there. Okay, MEM method solver is called integral equation. We have that one. And if you talk about the PO techniques like just PR plus solver, it uses a PO physical optic mix solver that can give you a quick result, because if you're going to solve this big structure in FEM-based solver, but and such a is a FEM-based solver by default, but additionally we added different solvers to ease your design process or analysis process. Okay, in that we have IE solver and SPR solver that both can be useful here. Okay, and you can place your antenna anywhere. Let's suppose you have a FFT file or NFT file here for and okay. You can use those files here. Okay, you can place that. That can see you. Okay, this is an particular antenna. Okay, and then you can see the performance of that antenna. Okay, you can see also the coupling matrix here. So these are the like different hybrid solutions. Let's suppose you have something and designed in FEM based solver like antennas in FEM, and you want to use on a big structure. There you need a hybrid solver that we're talking here. We are talking about. Okay, in that let's say you have a different hybrids, different solvers. Let's say this is in SPR plus, and then another one is in another in FEM, and another one is also in I. Okay, so this kind of simulation you can do using this hybrid solver. Okay, thereafter we are going to talk. This is one other case that I'm explaining. Okay, so this is a 5G base station antenna, and then there is a 4G base station antenna. So there are two antennas that you see here. Okay, 1 and 2. This is the past. So and then you want to calculate the antenna patterns. Okay, so these are the different coupling between the 12 base stations there. Okay, this here this number of 12 there, and then how it's coupling between the two number of antenna you can see here. Okay, and low to high, high to low, high to high, low to low. So this kind of coupling you can see here, and there like it will say like number of different antennas there, 4G, 5G, and all those things. Okay, thereafter one concept is that let's say there's a mechanical housing or maybe a dome structure on that. How it's going to impact that one also. You can see that one. Like let's say you are going to place your round structure, and then also you want to see how it's going to change. Okay, so let's say if you want to see black and like antenna in a free space. Let's say if I'm antenna is with the housing and the dome. Okay, how it's the antenna pattern is changing. You can see in red. Okay, then in blue antenna housing, if there is a PTD and UTD method techniques or like SPR plus techniques are used there. Okay, so this is the how you can see the different what you say level of analysis. Okay, like different pattern, how it's going to change it, the housing, how it's going to change it, exactly 5 PS event somewhere on the big mast or kind of those things. Okay, so this can be useful also there. Thereafter, one network planning coverage, or you can do this one. Okay, so let's say explaining some example here. Okay, so position 1, position 2, and position 3, and then how it's changing this at this location. So you can place whole map with the 3D geometry using city mapper, one of the available that can provide you and 3D geometry of a whole city. Okay, you can place the antenna using SBR plus solver, and you can place that antenna. That what do SBR solver? It paints the what do you say, the fields there. Okay. So this is one of the technique how is the fields are painted there. Okay, electrical currents. So and then you define your position 1 and position 2 1. Then you can see how it's changing antenna to antenna coupling. So this kind of analysis you can do, handoff and all those things, kind of analysis you can do. Thereafter, let's say you see one example here. This is one moving station. This is one base station. So how it's changing, how the hands off is going. Okay, so this is one different kind of the concept that you are going to try there. So you can use this type of methods there. Okay, to do this analysis. Then if you see here one example like between base station and base station 1, how the coupling going on. Okay, and like let's say cell tower handoff, how it's going there. As I was explaining, the starting slide I was explaining how the hands off and this cell tower off is going to be there. Thereafter, we need to talk about this emit because we shifted to this one from this and this and then this. Okay, so this is a one tool called emit. You can use this as you can define number of radius there, whatever the radius if you have, and then you can see RF cosine and interval analysis you can do there. Okay, then antenna coupling analysis you can do in SPR plus solver. Okay, and then there is a number of applications that can be useful to do this one. Let's if once I go in this tool, we are going to go in few seconds, okay, or maybe few minutes. So there I'll explain you different tools, different blocks there, how the different tools are there, toolkits available to do analysis. Thereafter, let's move on this. Okay, then this is also one link margin interface analysis scenario. How you can do this one. This is from one building and Bluetooth antenna is there. There is a Wi-Fi antenna is there. Then VD antenna and all those things. Okay, how different antennas are coupled to each other. How is they are performing? How the performance is degrading. All those kind of analysis you can do. Okay, there. And this is one system how you define an RF system in an emit. Okay, and then you will get a number of radios there. Whatever the radius is going to look, you will build your system. You can see the OSAT interference there. Okay, so this is one example of link margin versus distance. How the distance is changing, how the interference is changing. Okay, so sorry for this. Okay, so it's a link margin between stations and mobile devices. So if you see without interference, it's there. Yeah, but if you see with the interference, like there's a number of antennas there. Okay, so in that you can see how the performance is degrading. The link margin is degrading in the device and mobile station. So this is how you can and do analysis or do understand how your device is going to perform there in real scenario. Okay, then that's one thing, and then thereafter we are like we are going to talk about the multi-physics there. Okay, yeah. So this is the one example like 4G station. Okay, so let's suppose you have an antenna. Okay, in that this antenna is like 5+1 dipole array of antennas. Okay, and 40 watt input is there. 4 watt RF loss is there. Okay, EM loss that I was talking about. And so, and on that you want to do a thermal analysis. So what you can do, you can use ANSYS workbench there directly to plot the thermal loss, EM losses in thermal behavior there, and you can do thermal analysis, steady state thermal analysis. But before we are going to do that one, you can do in ANSYS HLS also, or ANSYS ISPAC. Okay, so this is one electrothermal analysis of a 5G base station example. Okay, so 8x8 dipole antenna is there, and what is the specific there. So we are using ISPAC classic here. Okay, and you can see the temperature analysis, how the temperature and deposition temperature is increasing there. Okay, so this is the maximum temperature difference you're going to get, and the EM loss that you got there, material what you use there, and ID. So what are the changes? What are different maximum temperature you want to test there with the EM loss? That can be seen here. Okay, there after okay, so this is one like the same example that we are going to show. Okay, and how we are going to see the two-way coupling here. Okay, so this is the like after thermal loading, what was the the loss, or maybe the the gain there. Okay, and then before loading, thermal loading, after thermal loading, and all those things. Okay, and also with the different theta, what was the theta degree at 0, at 90, what you going to get the gain there. Okay, so there this is the one that we were explained this graph there with the interference before thermal loading, all this thing, and with thermal loading, and with interference and after thermal loading. So this is the differences in the analysis or the pattern you're going to get there, in terms of link margin, how the thermal is also going to change your link margin, and how the structure also is going to change. So and the link coupling between the two stations. So this can be seen there. Okay. Okay. So let's say we are talking about the 5G, and in that we mainly the requirements is CDF versus EIRP. Okay. You want to do what is the cumulative disturbance function there, and what is EIRP, like radiative power is there. Okay. So these parameters you want to get there. There is already a toolkit that can help you to get these parameters, PD and CDF and all those things. So let's say one power density is also, you want to get, okay, what is the beam forming power density required there, how the power is going to be there on the planes, okay, on all operating bands of the 5G there. Okay, so you want to do this type of analysis, you can do these ones. Okay, and there is also already a toolkit in ANSYS HFSS 5G antenna toolkit that can do all this. You don't need to do further analysis to in another tool, or maybe another toolkit there. Okay, so this is the requirement of 5G PD. You want to solve, you want to calculate, you want to calculate CTF. Maybe there is a tool that can help. I'll show you where you will find that. Okay, so this is one toolkit. It's called HFSS 5G toolkit that can give you CTF versus EIRP. Okay, and then also you can calculate the power density and all those things there. Okay, so you can plot the PD and the coverage, and then you can see the results in terms of gain. Okay, so I'll show you where you're going to get these things. Okay, so this is one beam phase and concept, how the beam form is going to change, how this parameter can be applied there in ANSYS HFSS. I'll show you how you're going to find this parameter, how you can change that one, or maybe if you talk about the upper certain taper techniques, how you can do those things. Okay, let's say we are talking about antenna optimization. Okay, this one is like antenna design and optimization. So this all like grid cell and array arrangement, we can do it in ANSYS HFSS EM solver, FEM solver. Okay, and in that, okay, symmetry and all those things, you can do this one. And then if you talk about the 5G toolkit, HFSS 5G, it's already in ANSYS environment there, but toolkit that can help you in this to get this step 3 and step 4. First PD lower, and then a specification. Correlation is there, then you again go and change the PD of another. You want to do further analysis of kind on the 5G base. So you can do this thing in antenna design optimization. Okay. Thereafter, like the computer resources that you're going to use, let's skip this part because mesh fusion technique is there. If you want to know more about this, you can write me back again. We can discuss on that. Okay. So this is one automation workflow for an antenna of ECE. So we are talking about up to this, how you can do this thing. Okay. So beam staging table is there, AEDT unit cell, you get a unit cell, and in kind data simulation, you can do that one. From there, you can get the gain data and plot processing. Okay. And if you want to do finite array construction and simulation, then there you can do again data, and then you can get also the beam steering of each. You can do this one. Okay. And then you can also plot active as parameter versus beam and steering angle. Okay. So how you're going to steer the all angles, I'll show you. Okay. Thereafter, we are talking about this thing. Okay. Okay. So we are talking about then you can do automatic SPR setup there also using PyDT. This tool, there is a API based everything that can be done in PyDT. Whatever you are going to do in ANSYS HFS, you can do it in PyDT also. Give me a second, please. Okay. Okay. So this is one concept, like how you can automate your like automation of your antenna and 5G antennas that can be doable there. Okay. Further, like if you want to do link margin, all those things, that is also doable, but you need to think more on that. But this can be automated already. Okay. I'll explain you. I have read. I have wrote one, like one blog that explains you how you can automate the antenna design things. Okay. Also how you can you can use different AIML techniques that is also feasible. Let me show you, give you one. Okay, so you can, once you have a time, I'm pasting it in the chat box. You can where is this? Okay. Okay, so this is all about, we are going to talking only the presentation thing, and what I have explained you, we are going to see it in ANSYS in on the tool. Okay, so that's all in this slides. Okay, allow me to change my slide to go to my tool. Okay, in that. Okay, so I think, okay, I'll stop sharing this screen. Okay. Okay, I hope my screen is visible. So let's say I just, okay, so this is one design that this is a tool I'm talking right now here. Okay, and this is HFSS. If you version, you can, I'm using 25 20 or 24 R2, and maybe I'll use also 25 R1 ADP 2025 or 24 R2 going to use. Okay. It's not open access, but of course, if you are a student, you can use a student version there. It's available online. Okay, but few features will be not available. Maybe what the features I am going to explain, the toolkits. Okay, some will be not available there in ANSYS student version. Okay. Okay, so this is our the tool we are going to talk about here. So this is called ANSYS electronic desktop. Once you open it, you will get here as like this. Okay, and that you have to define which tool you are going to use. Okay, ANSYS HFSS. We are talking about antennas. We put it in ANSYS HFSS. Okay, I'll explain you Q3D circuit emit and what it is. Okay. So in that, let's say we are going to start with the basic design. Okay. So once you want to create a unit cell, okay, how you can create unit cell? As I was explaining you, there's a toolkit that can help you to get a basic unit design. Okay. So what I'm going to do here, we are going to use toolkit. You go in as a ANSYS HFSS, just click that one, view and ACT extension. So we say it ACT extension. In that you will find different number of tools there. Okay. I'm just waiting for it to be opened. Okay. 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 So here I have in this with SCT extension you can install number of tools there. Number of users are already available in ANSYS. Okay. But I'm going to use this one ANSYS HFSS toolkit, antenna toolkit. Okay. We have also this one 5G wizard. You can that later you're going to use. But this is how you can calculate your CDF here. You use this to click on this. Okay. And you just define the antenna design, what setup you, if you and you need your code book, you have it, okay, in CSV format, and then you define other things, and then you can get those things. Okay. Let's say go it back. Okay. Just click again. You close it. Exit this wizard. Yes. And we go it and HHHFSS there. And I'm going to use an patch direct antenna, like backstreet patch antenna. Okay. To get an basic design and how you can apply and boundary conditions there. Okay. So we will get let's say fed. Okay, let's be able to take this one. Okay. Okay, I'm talking about let's say 0.5 meter IPC. Okay, and just change the material, whatever you prefer, set size, thickness. Okay. Okay, you just close this one. Now, if you see here, you have one design of the antenna. Okay. And if you see here, all the things are applied already, boundary conditions. Okay. Citations. Okay. And if you see in that section type, hybrid. Okay, there's auto open region. What you can do, I'm going to do, because I don't need auto open region, I can click this one and I'll get a box. Okay. Here as a auto open region, I'll delete this one. So I have basic antenna design, that's why I'm unable to do this, what I'm looking for. So I want to show you how you can use and create an antenna unit. Okay. And that how you can create an array of antenna. Okay. So here we need a periodic boundary conditions here. Okay. So we'll select this one. And then what we will do, we'll right click on this, assign boundary, coupled, and auto file display. So if you see this, everything is applied. Let us pair 1, let us pair 2. Okay. And then you can define your boundary conditions. Okay. Let's say your this one is this. Let's say radiation boundary, you can keep a flow report also. Let's suppose if you're talking about a meta surface antenna, you can use that one. Okay. So here, okay, now we are set everything. Let's okay here, and I'm going to create a right click on this, create an array, option is there. Okay, so what it's doing is FADTM technique. Okay, finite array decomposition technique. So if I create an array, right click on that. Okay, you define the, you'll get this dialog. Okay, also what you can do, you can also use this option to create an array here. Okay, you just define the lattice pair and lattice pair around. Okay, lattice pair to, like, let's vector 1 and vector 2. What is the different axes there? Okay, you visualize this. Okay, and then this is the parameters that you're going to, you can define it as a active or passive. Let's say you want to define it as passive, define it as passive, or maybe you can define it as a padding. Okay, so this all can be applied here. Like, let's say I want to create an 8x8 or anything, or 5x8, you can create anything there. Active cells you have to define. Okay, and then post processing. So just apply, you will see the array of your NDRs. Okay, so this is how you can create an array in a quick way. Okay, let's suppose you have a you have already a unit cell defined. Okay, so this can be doable, can be done in quick way to get an array of antenna. Also, this is really useful to solve in SSS, HFSS. So what it will do, it will solve the, it will not solve every block of, it will solve one, and then it will use entire the solved matrix to give you a finalized result. But if you do it explicitly, like let's say you have created one unit cell and you just copy paste it here next, like copy pasting and copy pasting. So it will get number of inheritances. Okay, and then it will solve each unit cell there, but it will take your time, computing power and all those things. Okay, so if you want to reduce your computing power, you want to reduce your time and all those things, you can use this create array method. Okay, thereafter, what let's say I just deleted this one array. Okay, this is unit cell. Okay, so uh, how we can create a, like, I can delete this one. Okay, now I have a still unit cell, and what I can do, I right click on this. Okay, I'll create and create 3D component, or maybe just control A with this. Okay, right click place with 3D component. Okay, so what it will do, it will create a 3D component for me. I was talking about CADDM technique. This is the CADDM technique. So you create a 3D component of that. Okay, I'll show you what is another benefit of doing this. Okay, so now if you see this one, there is a, in that there is a 3D component, and this block is already there. And what I can do, create an array there, and define lattice space that I'm looking for. And now if I see, I can use the same method there. Okay, so I can apply and apply this one and visualize this one also. So this is how I can create this thing, create an array surface there. Also, let's say if you want to apply what do you say, a beam steering techniques there. Okay, so how you are going to apply here. Okay, so you know how you can use a toolkit that is called beam array antenna toolkit. So we go in tools there. There is what in this HFSS toolkit, and then there is a this toolkit called finite array beam array. Okay, so once you have an array of antennas, okay, in your design, this toolkit can be useful to define the, what you say, change your sources to beam steer your array of antennas. Okay, and in that there is a different options, like at what frequency the scan angle should be, theta and phi. You define those things. Okay, if you want to vary the phase shift, like you define this angle. Okay, phase shift in A, phase shift in B. Let's say I'm keeping it 0 because I'll calculate this one. Let's say you can will be anything there. Okay. Thereafter, what you can say, if you want to apply aperture taper. So let's say it's a flat. Okay, if you see this aperture taper of taper is that's what is the weight of it is there of the power. Okay, you can see this one. Let's say you were talking about the different. There are different aperture methods you can apply that one. Okay, and once it's done, you have set down on everything. You can what you can do. You can also do a create source group. Let's say you are talking about the large number of antennas. Okay, and that if you create group source. Okay, source group that is helpful, that can apply each steering virtually. Okay, so these are two different things. Let me explain this. I'll click on this. Okay, so it will create. Okay, let's create those things. Okay. Okay, so I just click on done. What it has done for me. So let's say this edit source has been modified with the post processing, and the results are applied all everywhere wherever the beam stair it can affect it. Okay, so I have done it, and now the toolkit work is finished. We don't need that toolkit because we wanted to apply the the phase angle and changes. So once you click this one, okay, what is it has done for you? It has added this thing, scan theta, scan phi, and all those things are these variables. Okay, so let's suppose you want to apply some theta and changes in some theta. Let's say you want to apply 30 degree. It will apply 30 degree. Just click on there, apply 30 degree there. Okay, so once you solve it, okay, so once you have solved your area of antenna, because I can solve it right now, but it will take time, so I will not start it. I have some examples I can show you. Okay, so this is let's see if you see this one. Okay, here the area of antennas there, and if you see the edit sources there. Okay, so edit sources, in that this is the changes that you're going to get. Okay, so how if before doing your area of antenna, there is a different fields for there. Like, so there was no scan mag, scan phase, and all those things that are not applied there. But what the scan beam angle toolkit has done is, let's say you use this tool one, okay, finite area beam angle. It has done addition of this phase angles. So how the phase angle is going to change once you want to beam steer it. Okay, so this is the technique, and then this thing, once you applied this thing, it's all applied. You don't need to change anything there. Okay, if you want to change, of course you can change it, but then everything will change for you. You need to know what you want to change them. Okay, and thereafter what you can do, you just apply your phase angle, scan frequency, or anything there. Okay, and you see what is the result is going to be there in the return loss, in the term of anything. Okay, so you can see as I haven't run this simulation, so that's why I'm getting blank. Okay, so let's say we'll close this one. I'll show you one example in my another tool that has been here. Okay, so we are talking about the 5G antennas. Okay, this one, if you focus on this example, this one is an example that is simulated at 26 gigahertz. I think that is a little bit like higher band. Okay, in that okay, so what is this scenario? I'll explain you. So we are talking about the scenario, an antenna, an array of antenna is there. Okay, on top of that there is a radome on that. Let's say you want to keep the radome for protecting from environment, or maybe you are going to the result can be performed because of that analysis, or maybe the performance of that antenna can be changed a bit. Okay, with that radome. So you want to find the effect of both things there. Okay, and this is how you can create an array of antenna that I explained you. What they use, they created a 3D component. Okay, now they are modeling it as an array. if you see this one, okay, this is my array of antenna. So this is one particular unit cell for me. Let's say I do a control D and then it in terms of a top. Okay, so this is antenna for 2 cross 2. You can say that, okay, 4 antennas are there, and the unit cell 4. Okay, so if you check this array, this one. So what they have done, they use this 3D component, React in 3D one as lattice pair 1 and lattice pair 2. Okay, and that they're defining the array of size 2 cross 2. Okay, thereafter what I'm doing here, then once like you are using a 3D component array. Okay, so this is the benefit of using 3D component array. Another benefit is like you can get the component and you can add number of components here. I'll show you one example how these things can be done. Okay, so we applied this one. Now if you want to change the direction and expand an array and all those things, the different options you're going to get. You want to rotate your component, you can rotate it also. And then active passive, you want to define anything you can do this one. Okay, so this is the where I'm showing that, okay, how the unit shell and array can be used. Okay, so now we have this. Okay, and then boundary conditions array. These are the boundary conditions. Okay, and excitations we are sources. So this is the excitation with the beam steering. Okay, how the beam is changing. Okay, and thereafter if you see this, the results, like let's say I'll show you how we are solving at 56 degrees Celsius at 2 passes. Okay, and then this is the gain. Okay, so we max we are going to getting 8.84, and what you can see, these are the number of, like, you can see the changes there. After what you can see, let's say you want to send changes in the data, you can change up to 20 degrees here. Okay. See that how this gain is also changed. So you can see how theta and phi changing the beam steering concept there. Okay. Okay. So so if you change the phi at 20 degree or maybe 50 degree, let's say. Okay. So how the things are changing for you. You can see this one, and then nothing changes there. But if you change the theta, it will change. Okay. Okay. So this is one thing how we can see the different parameters there. Okay. Gain plot is the one thing when you talk about the arrays. Okay. And you can see this one. Okay. Let's say you want to see it in modular. Okay. How the, so here if you see this one, you can see this here, and on your whole antenna how the radiation pattern is going to, how in which direction is going to radiate. So this kind of analysis you can do this one. Okay, and thereafter what you can do animate those things, animate it using the particular frequency or maybe a particular phase changes. Okay, you can do this thing. Okay. Okay, thereafter this is one example of an 5G antenna. You can see that a small example can show you how you can do this one, how you can go get up to this level, like with the unit cell to the area of antenna, then further analysis. Okay, so this, and thereafter whatever the simulation you have done here. Okay, let's say I'll just disable it. Okay, whatever the simulation you have done, we added it here as a 3D component. Okay, we treating with the radome right now. So this is area of rectangle. This is also an area of rectangular. Okay, but in that what it is there is a radome on top of that, and this same thing is there. So how this radome sector is going to change, you can see this one, and then again we are creating an array, same concept. Okay, and this hybrid agent is defined. How you can define the hybrid solutions are there in NC's HFS. This is one example of hybrid HFSs. So how the DOM is used in SPR plus HFS high SPR solver. So this is the, if you solve it in an FEM solver, HFS solver, okay. So it will take too much time, computing power. If you have it, if you don't have it, of course you need to use SPR plus. But it's really big, you know. So this is how the different two solvers are used here, like FEM solver for antennas and another for SPR, this for radome structure. Okay. So and see, you can see this one, how the gain is changing. Okay. So at 90 degree, at 0 degree, what is the gain changes? Okay. And so that's how it's going to change. Okay. So this is one example of how you can get the unit cell and all those things. Proceed with the simulation. Okay. Okay. So and then one thing is that, okay, so this one example. Okay. Thereafter, we are going to talk about the meta surface antennas. Okay. And in this, what I'm going to explain you how you can get an unit cell. Okay. So this example, if you see, so this is one example, and if you're talking about the what do you say, meta surface antennas, in that what do you say, it's a particular you need to use a floquet port. Okay, how you can define a floquet port? Of course, this excitation. Right click on this, you go port, you define the floquet. Okay, you just need to select your geometry. So how they have done it? How an example can be created using a floquet port. This is one example. Okay, so in this, if you see this structure or unit cell, okay, whatever the format, you can define anything here. Okay, and additionally, what you can do here, okay, additionally on top of that, this is like a unit cell. On top of that, a floquet port is defined. Let's say if you see, okay, just repeating. So there is an excitation on the bottom. You can say that a wave port, right? Yeah, okay, and that is going to connect it on the top of this what do you say, this sheet. Yeah, okay, and then there is a floquet port on top. Because if you talking about the what do you say, array structure, and in that you need a floquet port. And mainly if you talk about the meta surfaces, you need to use a floquet port. But even also radiation boundary can be useful, but not for the large structures. Radiation also boundary can be included. So you need to use a huge periodic boundaries there. Okay. In this unit cell, if you see this one, there is a periodic boundaries are applied. Okay. Perfectly for whatever the copper sheet we have. Okay. Let's say you don't have a copper sheet. You whatever the perfect electric is there, you define that one. Okay. And if you see this structure, okay, there is a radiator on top of that, like there is a bias that we use to connect this one. Okay. And then in this box, let's say this middle of the box, closest box. Okay. And we are creating a vacuum to radiate do the analysis. Okay. And then box H is there. Okay. So here, if you see this one, okay, so all this analysis has been done. Okay, and if you see the parameter of this S parameter, so this is the S parameter. This is S11 and this is one S21. Okay, so for the floquet port, you can just see this, and this is how you're getting 12 dB around something. So you want to improvise this one. Okay, so there. Okay, so this is as parameter block, and this is the outcome of that unit cell that we have designed here. Okay, this simple unit cell. And if you want to see this example, you want to find this, I'll show you where you can find this one. Okay. There, if you see, the ports are defined, then other things. Okay, so we are going to use this unit cell as to create an array of meta surface array. You can say this one. If you want to talk about the reflect array and all those things, there is an antenna toolkit that is here. This toolkit can help you to create an array of like, let's say you want to create a reflect array, or let's say thinking about meta lenses. You want to create what you say terahertz antennas. Okay, and then you want to use an OEM technique for the meta lenses. You can use this tool to create whatever the meta surface you're going to look for. You just need to define your unit cell here. Okay, phase. Okay, and then feed coordinates and everything, and then you're going to get your just create it and get it. Okay, so this is one this is one tool that can be useful. Okay, thereafter this unit cell, if you see this one, okay, this is unit cell. Okay, we are going to use this one to create an array. Okay, so this array here, sorry, this was the next step. Okay, so here we are using one 3D this unit cell. Okay, this is our one design that was unit cell. We created the 3D component of that, and here you're using is 3D component. Okay, so in that, if you see, we are creating an array using this unit cell, and this is the unit cell of 5x5. Okay, and this meta cell, everything is calculated there. Like, let's say if you talk about excitation, you are using unit cell excitation. In that, there's a flow keyboard, so you're using that one. Okay, and then we again analyzing it at 3.2 gigahertz. Okay, and these are the plot. Okay, so let's say you are getting 9.7 maximum gain here. Okay, but if you see in unit cell, we want to talk about this parameter here. Talking there, so we can plot that one. We just right click on that. Okay, have a radiation. We don't have, so we can plot that. Okay, so we will talk about this one here. Okay, so the gain is improvised with maximum 90 dB. It's really great for the, if you talk about the meta, in terms of antenna. Okay, okay, so how the this gain, what you say that you can use create an array of meta surface of meta surface antennas. Okay, now let's say you have a meta surface antenna. Okay, but you want to place it on a particular plane or anything, any other thing. Okay, there. So we are using as excitation. What you can do, right click on this, create a component by file or near field. You can use anything there. Okay, or maybe you can link source design from here. So as a 3D components, antenna is there placed on a particular cockpit, I think. Okay, and on the bottom of the plane. Okay, and see what is the antenna performance there. Okay, installed antenna performance. Maybe suppose you included 2 antennas there. Okay, so you can do such type of analysis there. Okay, and let's say you just need to define your antenna, whether it is a TX or RX. Okay, let's say it's like TX RX. You have to define it as a, let's say your transmitter or receiver. You can define both TX RX. Okay, this matrix will help you to find the coupling between 2 antennas there. So gain, okay, the simulation was not ran, so that's why we're not getting from the yet. But the particular changes that you're going to get because of that that plane that is installed on a plane, you can see here by plotting a gain here. Okay, so this is how you can do analysis of plotting or meta surface and all those things. Okay, also if you want to see let's say you want to see MIMO antennas there. Okay, so if you see this MIMO antenna. Okay, so there is a 8 loop antennas are there. Okay, and they are using as a MIMO interface. Okay, and now you in MIMO, if you talk about what you want to, let's say you want to talk about uh, the correlation coefficient, you want to talk about the directivity gain, dark, and CCL, and all those things. So there is a toolkit. Let's suppose you have designed some antenna here. This MIMO antenna is there. Okay, and you have a different excitation for all. Okay, and in that, what we want to calculate, let's say we calculate the 3D gain of this, we calculate other as parameters. Okay, but what do you want to find? We want to find the correlation coefficient. Okay, so here what you can do, you go on automation. Okay? You go on automation, you find this MIMO toolkit in ANSYS. I think 20 after 22 or 23 version you can find those things. Okay, but I'm using it in 25 R1, R2, 23 R2. You can find all. Yeah. So this MIMO, you click on MIMO toolkit once you have designed. Okay, you will get this toolkit like this. Okay, so in that, you suppose you want to find the coupling between two, between two ports there. Okay, so you have to select two port you want to calculate. Okay, theta position, and then the solution, and which frequency you want to. Let's suppose you want to give like number of frequencies. Just need to select all the frequencies and just generate it. Once you generate this one, what will happen? It will create a data table like this. Okay, that is blank, but I have to run it once again. Okay. But what you can do, you can click there, you can get the correlation coefficient of that particular two ports. Then, okay. Let's suppose you want to plot the diversity gain. You will get two parameters there. You can plot the correlation coefficient and diversity gain. Just need to select what you want to plot there, diversity gain or correlation coefficient. But by default, the correlation coefficient will be plotted. From here, once you modify this to common outputs, okay, you define the, you just click the diversity gain and you, okay. So this is how you can use the MIMO toolkit to define your parameters there. Okay. Abhishek Karwa, please write your question there. Okay. Okay. So this is one example there. Okay. And yeah, that's all. That's all here I'm talking. Okay. And one thing I wanted to show you one example. Like I was talking about this toolkit, CATTM taking mainly on. Hi Banu, what you can do, you can export directly whatever the result. Let's suppose you want to plot, you want to use it for publication and all those things for a good relation. Also, you can use from here. You can export it. Let's suppose we were talking about this one that you can see. Right click on this, export it as a CSV, and then you can export it as whatever you're looking for. Maybe CSV. What you can do, you can export in CSV. You can use origin tool to any plotter tool to plot this thing. Okay. Also from here, of course, you're going to get the result. Then you want to change something, you can change this one and export, copy as a bitmap image or anything. You can export anyhow. Okay. Okay. Abhishek, you can ask this question in chat. Thereafter, I was explaining one example here. Okay. This one. Okay. So this one, this example, if you see here, there is explicit method to copy paste. Okay. we explicitly copy pasted the array to create an array. Okay, but here if you see as a multi-cell, we created what we have done. We created the same thing here. Okay, one tool, this tool, another thing, and then we created a 3D component of that. Okay. So if you see this array, okay, it's got crashed actually. So yeah, I can show you in this another tool. Okay. Okay, it's got crashed. Forgive me for this. Okay, with that, if you go example, find this. Okay, any questions? Abhishek, yeah, what you can use Fabi, find just one for a seat using. Yeah, if you want to apply Fabi simulations, you want to do a Fabi, diagram, like Fabi boundary conditions you want to use, what you can do, okay, so I'll show you one example here. Right click on this. If you go in, you have to be in particularly, you just click assign boundary, what you want to apply. Fabi, you can click on that. And then you can, for further questions, you just, for if you have any question, please do write me. I'll answer you on that. Okay. But Fabi you can directly apply here, and then you need to use your, if you are in a hybrid condition, hybrid mode, you can use that one also. Yeah, that's all here. Like Fabi condition directly, you just click the boundary condition. Let, for example, a radiation boundary. However you apply, you can use in the same manner as a Fabi. Okay. Also, one thing, yeah, it's on in the mail you can see vivek.yadav@catfam.in, my mail ID. I'll write it. Okay. Also, yeah, for the installation, what you can do, you just find student version and you will directly download it. Okay. Okay, so this is one thing. Last I'm going to cover it here. This one is a one. Okay, so this is how you can create number of corners, sides, different cells there. You can use it to create an array of antenna. Okay, and this, if you see this array block here, okay, there is a one lattice there you define, but the unit cells are different. So one main unit cell is there, like 2 to 2. That is like let's say this is a radon. On top of that, we are there is a antennas. There is an array of antennas are there, empty cells and a early substrate there, and then cell radome are there. Like let's say main cell that you're talking. So thereafter, there's a radomaster. Everything you want to apply and create as a 3D structure or 3D array, you can use this tool as a 3D array also. So yeah, that's all from my side. Thank you.
Sir,
Yeah.
sir, I'm not getting this array option in my HFSS. Actually,
Yeah.
I'm using ANSYS HFSS 2022 R1.
Okay, 2022 R1. Okay, but
Yes.
what you have to do, you have to go in solution type and you have to be in HFSS with hybrid arrays. Okay. Did you get me?
No, I'm not getting your point, sir.
Okay, so once you go in HFSS, there is solution type. Okay.
Okay.
Solution type, you click there, and there you have to click need to be in HFSS with hybrid and arrays. Okay.
Okay.
Once you click that one and then just click OK. Thereafter you can create an array of antenna. Like you once you set the boundary conditions like periodic boundary, you will get an option. Right click on that, create an array. Okay.
Okay. Got it, sir. Thank you.
Yeah. Okay. Any other questions?
Any other queries from the participant side?
Hello.
Yeah,
Hello.
Abhishek, sir.
Sir, thank you. It was very nice presentation, sir.
Thank you, sir.
Uh,
Thank you.
Sir, actually, I want to use that Fabry boundary condition.
Yeah, right.
In which I have to take two horn antennas, and in between these two horn antennas, I will be placing my FSS surface.
Okay, right.
Uh,
Yeah.
so first, I want to know that how to get that horn antenna inbuilt feature. If there is any inbuilt feature in HFSS, that we can have that model of a horn antenna.
You can use antenna toolkit directly there, or there is a number of libraries like, let's say, like as I was explaining you, antenna toolkit that can help you get an horn antenna. That
So
can be used. Yeah.
maybe I'm confused. Like that, if the FSS is working in X band, 8 to 12 gigahertz,
Okay, right.
so the horn antenna should be of same range, or it can be of any wider range.
You can keep it wider range. You don't need to. What is your motive on using horn antenna there? You should know what you want to observe there. Okay.
So I want to observe that S21.
Okay, S21. So you want, but okay. So what you can do? You can keep a band also. Not a problem.
What can I keep?
A band of frequency. Like let's say you
Okay.
want different in a range of frequency.
So is there any link so that I can get a help in a video domain, or is there any?
Actually, there is no link, but what you can you can go on ANSYS help. There is there's a number of help videos are there. You can use that one. Just search
Okay.
ANSYS related HFS, something like that. You'll find it.
Okay, sir. Okay.
And then there is a ANSYS innovation courses are there. Innovation
Okay.
courses that also helpful. Okay.
Okay, sir. Okay. Thank you, sir.
Yeah. Thank you. Okay. So anyone else?
Any other queries from the participants? I think there are no more queries, sir.
Yeah. Great, sir. Okay. Yeah.
Thank you, sir. On the behalf of the participants and from the MIT Group of Institutes, I extend my heartful thanks to Vivek Yadav, sir. Thank you, sir.
Thank you, sir. Thank you so much. Thank you for
Thank you
giving
once
this
again for your
opportunity.
valuable time and contribution to this FDP, sir. You have
Yes,
very
sure.
well explained the HFS of software,
Mhm.
mathematical unit cells. Very well explained, sir.
Yeah. Yeah.
I
Okay.
thought
Yeah.
it's very benefit to our participants, sir.
Yes, sir. My motive was to let them understand the tools and technique, then
Very
they can
well.
apply everything.
Very well
Okay.
explanation, sir.
Okay. Thank you so much, sir. Thank you for giving this opportunity. It was really nice discussing here and all those things. So yeah, thanks all once again,
Thank you.
and have a nice day, you all.
Thank you, sir.
Yeah, Hina, you can use innovation NSYS innovation courses there. That there's a number of libraries and courses that can help you in there. Okay. Yeah. Thanks. Bye.
Thank you, sir. Good day.
Thank you. Yeah.
Our next speaker, Vivek Bakshi, will join us shortly.
Hello, sir.
Yes, sir.
I'm
Have you joined, sir?
Vivek Bakshi. Already joined, sir, but sharing part this side not allowed.
Okay, okay. I will make you co-host, sir. Actually.
No need. Already I joined. Exact 3:30.
Yeah, okay, sir. Thank you, sir. Moving ahead to our FDP program, we are honored to have with us Shri Vivek Bakshi, sir. Sir is a senior application engineer at Jyoti Electronics, a IEEE member, received his MTech degree in microwave electronics from University of Delhi and MBA in finance from Indira Gandhi Open University. Prior to joining Jyoti Electronics, he has 5 years of experience in design, modeling, and simulation, having experiences on various projects like design and development of SSPA, antenna array design for phased array, Doppler radar. His current research interests include cavity filter design, hardware neuromorphic computing platforms, hardware security primitives, novel devices architecture for RF photonics, analytically and compact modeling of semiconductor devices for volatile memories, TWTS, and various microwave terahertz devices and modeling. Sir, on the behalf of the MIT group, I welcome you, sir.
Okay, so thank you so much for inviting me for this talk. So first of all, good afternoon, everyone. So to all my respected faculties and those research scholars also who are joining this talk. So I am Vivek Bakshi, currently working in Jyoti Electronics, Bengaluru. So we are dealing with this CST Studio Shoot application. Just before that,
Sir,
I
pardon,
have
sir,
to
your
show
screen is not visible.
screen means our screen just I have shared, sir.
PPT, your PPT, sir. You're right.
Okay, okay. 1 second, sir.
Okay, sir. Now
So
it's
here, okay. So here you can see my name is Vivek Bakshi and our Jyoti Electronics is Ahmedabad-based company. This is around 35 years old company and we are channel partner with Dassault System. And Dassault System only we are handling three products. One is CST Studio Shoot and another is Abacus and Katia. So CST Studio Shoot mainly used for this circuit simulation, antenna, filter designing. For these purposes, we are using this CST Studio Shoot. And for Abacus is mostly focused on this mechanical aerospace domain people, those who are working on structural design as well as material synthesis, other activities they want to follow. So they can use this Abacus part. And third comes the Katia. So mostly surface modeling design, those CAD designing files we are using Katia. So these three products we are dealing with Dassault Systems and we are giving technical support also. And with this we are giving hardware equipments also. Now we'll jump into our principles. So we are dealing with, you can see it, Dassault System, this CST, Abacus and Katia. And hardware equipments like navigation equipments, we are dealing from IP Solution, one Japanese-based company, and rubidium oscillator from Precision Test Systems. And now we'll jump into, mostly we'll focus into CST Studio Shoot. So all our major customers in CST Studio Shoot are SAC ISRO, URSC ISRO in Bengaluru. So ISTRAC also, they are also currently using CST applications. And with these all major DRDO research labs in Bengaluru like LRT, CAPS, and LRT CAPS and ADA, ADE, everyone is using this CST Studio Shoot applications. So Bharat Electronics Limited, that PDIC Product Development Innovation Cells, so they are mostly doing the design part of this RF microwave hardwares. So they are also using for CST for this design analysis, and HIL Wing mostly for this transmitter transponder designing. For that they are using, and with this plasma level also some domain work you can handle it by using CST. An Ahmedabad-based central agency is there, that is Institute of Plasma Research. So their most research work is on plasma domain. So they are using CST Studio Shoot. With that, PRL Ahmedabad, like Physical Research Laboratory, ISRO also, they are also using CST for mostly for the structural design like microwave devices like laser gun diode, those things. Now we'll jump into this CST Studio Shoot. You can see CST 2025, how it's look like. So here the front view of CST 2025. You can see in CST 2025, whenever you start designing anything, you have to start from the scratch level. So first you have to click on the project template. Once you click on the project template, here different sections are coming, like microwave RF, optical, EDA, electronics, EMC, EMI, particle dynamics, static low frequency. So if you are interested for 5G level antenna design or metamaterial design, you have to click on this microwave and RF optical part. After that, you have to click it on this antenna section. Once you click on that antenna section, here you can see all those domain related like waveguide, all these mobile devices, 5G reflector, dielectric resonator, RFP, phased array, all these parts you can design it by using these sections. So next comes the circuit component part. Same to same, like antenna, if you are into filter designing also, you can use this part. So nowadays radar applications also you can use. So LID, DITU people, they are mostly working in this radar application part. And next comes the biomedical exposure. So at present nowadays, people are using CST mostly for this biomedical medical equipments. If you are developing anything in that, also for calculating that SR part like specific absorption rate and other heat, specific heat loss, you want to measure it. For that also, we are developing those equipments in CST, and through post processing, we are analyzing these all characters like SAR, exposure, these things. Suppose nowadays wearable textile antennas also people are using. Otherwise, those watches what you are using, those watch radiation, how much it will affect through your screen. That also you can uh, see through this biomedical exposure and SAR. Next comes the optical application part. So plasmonic and dielectric structure now means metamaterial issue work. So metamaterial persons mostly they are going into this periodic structure, and for this frequency selective surface like FSS, metamaterial and all those things you can design it by using this microwave RF optical. So antenna designing and filter designing is one part what you can do, but most people that don't know aware of that key in CSC Studio Suite, you can go for this PCB level. Some method like testing, you can do it like signal integrity, power integrity, those things. So those things are also included in CST. You can see those things you can handle it by using this EDA electronics. So this is completely related to PCB level, those people who are working like high RF PCB boards. So next comes the EMC EMI section. So EMC EMI, all those radiated conducted emission, generally people going to testing laboratory, they are doing all those tests there. But then you can do that part also in this CST Studio Suite, no problem in that. Next comes the particle dynamics. SAC ISRO people mostly they are working on this space application thing. So in that, all those waveguide component multiplication analysis they are handling through by using this space application domain. And acceleration component and vacuum electronic device also very important in space applications. So they are designing all this particle gone, magnetron, klystron, all those things, EWT even in this vacuum electronic device. So all those structure basis designing like EWT, microwave devices, those things you can do the designing part by using this section called practical dynamics. Next comes the static low frequency part. For this, we are having one separate module in CSC that is called Opera. Whenever you will open Opera, in that you can do all those part of designing like sensor magnet design, those part like suppose nowadays you heard about maglev trains, so those maglev train magnetic tracks also you can do the designing part here. Through that you can see how much this addition part is happening, and power electronic section in this PCB bus bars, like nowadays buses also automatically getting charged. So electric vehicle, those bus they need charge stations. So for the charge station you need bus bars. So bus bars also you can do the designing, transformer shows, these things. So almost this 5 modules what is very important in CST if you want to design from the scratch level. Now we'll go a little bit deeper what things are newly included in CST 2025 section. So here you can see we nowadays we updated one new module that is called WASPNet, mostly for this filter designing people, those who are working. So for them we included WASPNet last year only, and that Opera FEO what I mentioned, that is mostly for this low frequency design applications. And this IDEM also PCB related those little bit character you want to study for them. And RF breakdown voltage analysis if you want to study for them, this Spark 3D module. And Phase 3D and this filter designing, both are for specifically for waveguide based filter designing only. So you can see it in Phase 3D what things are there. In CST also filter designing what things are there. So in CST filter designing you can see, so all low pass, high pass, band pass, some prototypes are there. Suppose you want to design some cavity 3D model, so you have to click on that. So little bit if you go deeply, you can see how these things are working. So first, what kind of response you learned, like EP ripple or Chebyshev or Butterworth, the response you have to show here. And after that, how many orders, like nth number order, like 21, 25 orders, that level you want to do it. and that operating frequency, what is the starting and stopping point, those things also you have to very mention it here. After that, you have to go to the topology. So these things are comes under this filter section. When these things are done, you can see these kinds of design module. It will take generate. So once you click on the 3D model, it will clear the design for you. You have to run the analysis. So filter designing mostly works for synthesize couple metrics. This whole thing you have to verify. Once it verify, you can take that filter design model into CST. So that option is there in this CST 2025. They included it, and with this Flash 3D is mostly used for this waveguide based filter designing. So you are into waveguide based filter designing, then you can use this Flash 3D model. And next comes that CST Studio Shoot. We are having one module called Antenna Megas. So, sir, my voice is audible that side completely. Hello. So,
Yes, sir.
and voice is audible, sir. That side completely.
Yes, sir. It's audible, sir. Perfect.
Oh, okay, sir. So antenna megas, this module, you can see all the antenna part, what you have explained, that is 5G or 6G, all these things are included in this antenna megas. So around 2000 prototype antennas we are having. So these antenna prototypes we have taken from some research papers. So all those research paper we have followed, and from that only those antenna modules we have put it in these antenna megas. So earlier what used to happen in CST Studio Shoot, everything you have to design it from the scratch level, like putting one way, one like bricks, PR, everything you have to handle it. After that, designing part will be done like that. But nowadays, because people doing research more and more, so they are using this antenna megas model, what is comfortable for them. So you mentioned about 5G, 4G. So let me go with this smart device mobile communication. So in these different sections are there, like personal area network, like WiMAX, WLAN, these things. If you choose, select that part, here you can see different kind of antenna it's showing. So once you click on that antenna part, so it will show you all those antenna, what is there, prototype models are there in this CST. You can see all those things. So these are all prototypes. Suppose you want to design any, you mentioned about metamaterial. So metamaterial, if you click here, so this is, once you click on this metamaterial, it will show you all those listed antenna prototypes which is related to metamaterial. So here you can see all those metamaterial based antennas. It's now visible here. So suppose this one antenna you want to see how it's working. So you have to click on this part. So once you click on that antenna mega spot, let me go through here and explain you everything what is there. So here that antenna mega spot, what I have mentioned you, once you open that antenna megas, it will show you option like this. So here those all listed antenna megas, all prototype antennas. So once you selected your antenna, what antenna part you want to design, in that prototype antenna design part, you have to mention your frequency, at what frequency you want to design it. And that port impedance also you have to write it down here like this, 50 ohm here mentioned. So next comes that manufacturing part. So what kind of substrate, those things you want to use it in that antenna megas prototype. So there, if you are using Rogers, you can measure Rogers also, no problem. And the substrate thickness, those part you have to mention it there so that it will be easier. So here you can see one example we have taken in that Rogers substrate we have taken, and that Rogers substrate relative permittivity we mentioned around 3.27, and substrate height equal to 2.54 mm. After that, we are putting these things as a parameter wise. You have to mention those things also. What parameter, like some sketch you have taken, in that sketch, length, breadth, height, everything you have to mention it here. Once these things you mentioned there you have to press the estimate performance. So it will give you this kind of results like this all radiation results, everything. Once the result part is done, you can export that model into CST Studio Shoot directly. So earlier we people used to design this part like this CST Studio Shoot we are coming and project template we are using. After that microwave antenna we are choosing. But now if you are having antenna megas model, you can directly select everything like this. So this is one good thing they have added in this antenna megas module. If you want to save your time and want to do more or more research on this antenna part, you can design those antenna very easily by using this antenna megas module. So these things are there. So now we'll jump into PPT little bit. So here you can see same thing what I have explained you like CST Studio Shoot. In that CST Studio Shoot, that Spark 3D module I have explained. So Spark 3D module mostly people who are working in plasma level research they are doing for multiplexer analysis and gas discharge analysis. This RF vector voltage you want to measure it so that you are using this Spark 3D module. So this KBT filter designing those things you are doing it in CST Studio Shoot. After that we are putting that model in Spark 3D and verifying all those results. So next comes that Phase 3D model. Like I told you, for a waveguide filter designing these things are used. So this Phase 3D is mostly for this. And antenna megas just now I explained. So Opera like magnet level design, anything you want to do it for them, Opera. So Abacus is mostly for this thing. So now we'll jump into this part like what kind of things you can handle it by using this. So CST, if you are doing the designing part like antenna and some divider or something, you have to assemble that part. You can do it by choosing this like circuit and schematic. In that you can come to this assembly part. And once you select this assembly part, you can see you can drag and drop both section like this. So your view it will look like this. Like one thing you put antenna part you put it as a block. This block is connected to an external port. So these things all you can do by using this CST schematic. So schematic and assembly, these both part are very important. So here that schematic part, circuit schematic part. So they are having separate one device model library. In this device model library, all listed vendors, this register, inductor, all those things are mentioned here. So if any PCB board, if you have designed already and you want to put implant some diode and register or inductor, you want to verify how this result you are getting. So you can utilize this all device library by putting this diode. After that, you have to give here one task like new task. In this new task option, you can see all as parameter level result or AC result or transient result you want. Those things you can give instruction to CST key. I want this kind of result from this. So that thing can be enable. So here those schematic, if you want to have design this strip line based and this micro strip line based or transmission line based, all things you can do it by choosing like this. So this is little bit schematic and assembly part. And next comes this PCB and packages module. So in your colleague or friend circle of yours, if anyone is currently working on any PCB model designing, so they can also utilize this PCB studio part. So PCB studio part, if you are having token of this, then you can jump into this like some file you have designed in Cadence Allegro or some ODB++ file you are having or Juken or Mentor Graphics, those things. You can directly import those files and you can see those stack up analysis part, you can handle it. Like if it is a multi-layer board, layer by layer, every instruction you can give it in that thickness, conductivity and permittivity, all those things you can mention it. And next comes that component in that PCB board also, any component you want to edit, that part also you can do it. So mostly server what we are using in this PCB board, so that is like signal integrity, that is also in time domain and frequency domain it varies. Next comes the DDR4 analysis also. So this CST2025 they have added this IR drop analysis. So earlier it was not there, so just now they have added. So if anyone is working in RF PCB board level also, for them also this application is very useful. So I think if anyone is working on this, it will be very good. So here you can see that PCB part, what file we have taken in that we have done one signal integrity analysis part. So this thing, and with this PCB also you can go for cable designing also. Now their automotive section people, those who are working, they are mostly looking for this cable harness method testing. So those cable harness method also you can do the designing part like this. In that you can see after that cable part is designed, we put them that thing as a block, and that block is connected to all those register conductor and this external port. And after that we have measuring this crosstalk analysis from this cable. And next comes the solver choice part. So any time you are designing anything like in CSC Studio Shoot, like right now I have designed this like one MIMO antenna. So in this MIMO antenna you can see, so whenever you want to simulate this MIMO antenna, you have to start from the scratch level, like you have to go here choose this brick spot and all those things, and after that you have to put this discrete code and waveguide code as per your requirement, like current voltage calculation. If you want to do there, you have to use discrete code. Suppose others like parameter like far field radiation pattern and this electric field, magnetic field, if you want to measure, then you have to use this waveguide code part. So this frequency, all those things mentioned, and I have created one workflow for you where you can go and see these things, study these things, how these things are done. So MIMO part I will explain further in details to you. So no problem to think now. So let me close this part. So whenever you are choosing any CST simulation you are doing, so solver part is very important for you, because in solver only calculation everything is happening. Every solver having different computational mathematic technique. So here you can see time domain. Hello. Here you can see time domain solver, frequency domain solver, eigen, and integral equation solver. All these solvers are there. So you first have to know where these solvers are mostly used. You can use. So for that, I have this slide is very important for you. So mostly for medium large size, any structure you have designed and you want to have broadband analysis, for that you need to go through this time domain solver. So time domain solver mostly working in on this computational mathematical technique like TLM, and another is their FET. FET is means finite integration technique, and TLM means transmission line metrics. And if you're going for this narrow band calculation, for that frequency domain solver is enough. In that electrical small to medium sized structures design, mostly we are working that. And frequency domain, mostly we are using periodic structures like where you have to go for this boundary condition, and boundary condition you have to go for float and float analysis also. So these things you can do it. And suppose you are working on this eigen mode solver, like any closed like structure, cavity filter type of structure, there you have to use this eigen mode solver. And next come that extremely large structures like some aircraft model you are having with you. In that you have some antenna part to be placement you have to be do. In that section you have to use this integral equations and the RCS calculation. Those things if you have to measure it, then asymptotic solver is the best one. And last and the final comes that multi-layer solver. If you are working on multi-layer board, for that multi-layer solver is very important. And nowadays they have included hybrid solver also. Suppose you are having one SIP. In that SIP, one antenna is connected, both SIP as well as antenna, that both part you want to run the simulation. In that simulation, better to you have to use hybrid solver, because SIP part it will be very larger one, and antenna part it not need that kind of solver. So in hybrid solver, one situation is there where you can use both part. So when you come to this thing like here, you have to come here. One option is there simulation project. In simulation project, we are having one hybrid solver task. Both unidirectional and bidirectional, you can get that response as ever you want. So these things you can do it. So let me go through some topics like uh, jump into topics. So today, let me tell you what things you can do it in CST. So this is the server part, which is very, very important one in thing, and all those things, what is I explained to you, that thing is very important when you are going for design simulation part. So next comes that mesh analysis. So whenever any structure you are designing, it will break into small, small meshes. Like time domain solver you are using, then hexagonal mesh is very important. You have to choose that option. It will be there in this. Like whenever choose then you go and time domain. Here you can see that solver setting. Two options are coming. One is a hexagonal fit and hexagonal TL. So if you're using hexagonal feet, it will give you different type of mesh view. Like mesh view option is here in this home tab only, and this home tab, all those things comes under this ribbon bar, and you can see how many cells are there in wavelength. Are there like 15 we have taken here, and cell for box list is there. So if you want to update that thing also, sometime if you run a simulation, that simulation showing error like meshes error, like then you have to select this global property part. There you have to decrease, and after that only a whole structure can be simulated. So those things are very important. Here you can see that mesh cells options are showing here around 1,32,600 mesh cell is there in this MIMO antenna designing. So this is the part what you are telling why mesh cells are important. So next comes that frequency domain solver. If you are using, there you have to use this tetrahedral mesh and surface mesh as per your requirement. And next comes that help section. Also you can take it like this. So these are all component library list. Those things are not needed for you that much. So here, just a common overview what things are there. First, you have to think like your concept should be developed, idea should be developed. On the basis of the idea, you have to think what kind of uh, component part we have to design. Once that design part is done, so you can go for UM simulation. EM simulation give you proper result. Then you have to go for prototype, and prototype, after that this final product is happening. Same to same like this, we have created one like power splitter you can see, and in that power splitter all those numerical method like solvers we are using, and solver settings also discretization, boundary boolean, frequency range, all those things, and from this we are measuring the results. So simple overview what I told you just few times back, how you can go for from the scratch level like project template. In that this antenna part you have to select, and here this tab bar is known as ribbon bar, and left side this bar is known as navigation window. Here the parameter list and all those things. So these are the important things whenever you are doing designing from the scratch level. At that time you have to use these primitives like cylinder, sphere, brick, elliptical, coney, and this everything. So these options are there in this when you go for modeling, and you see this kind of options. Like all these primitives are listed here. So for this designing, we have used this brick part little bit and all those things. So with this one pick options also there. Whenever you are doing any design in that, you are selecting any phase. So let me go again into that PPT. In that PPT, you can see this kind of view options are coming. So this is like cutting plane views. So if you go to that ribbon bar, in that ribbon bar, one view tab is there. In that view tab, you can click on this all options like working plane options. There you can do little bit modification also, no problem. So if you go a little bit deeper, then you can understand. So if people are today we wanna discuss about material part. So material part is very important. So CST having one separate material library. Whenever you want to design anything, you have to select that material. So material, you can see all listed materials are here. Suppose this listed material details like reflective, permittivity, dielectric, everything is mentioned here downside in this attribute section. Suppose you want to add some new material like that is not listed in the material library. For that, you have to click on this new edit option. After that, here you have to mention that material name. In that material name, this epsilon new value you have to enter. And if that material having some special character like thermal dispersion, those things are there. Those things also you have to mention it here. Once it's done, then you can add that material in this material library also, that newly material what you have synthesized. So that is one option is there in CST. Uh, after this, other things like suppose you have created one brick and spear, those things. So I told you earlier, this is we have taken one example of brick. In that brick, you have taken key, you have to choose one point. So you have to select, you have to come again to this modeling tab. In modeling tab, you have to select this peak. In that peak, we have to select this edge. So this edge, you can see we have selected one picked edge here. And suppose you have clicked F, then it will select one test here. So all those coordinate things you can see in the left hand side of yours. So this is the peak part. So after the peak section is done, you have to set that working coordinate system also. So these are the all working coordinate system. This option also there in this CST. Just you have to go there. Here you can see one local WCS option it's showing. Suppose in that plane you have to align that WCS, you can click it here. And suppose you want to change that plane view also, you can change it. Like so here you can change this as per your requirement, like XY plane or XZ plane, that working coordinate system also you can change it. There is no problem in that. So that is the part from the working coordinate system. And here some example like some working coordinate system you want to move, like rotation also you can do it, translation also you can do it, that part you can do it. So next comes that Boolean operation part. Suppose in designing you have taken one brick and spear, that brick spear you want to edit, then those kind of operation you want to do it through this Boolean operation only. Add, subtract, intersect, this insert, trim, these all option you can use it for designing those things. So modeling is very important. In modeling, suppose some complicated structures are there, you have to design some COPs. Those COPs part you can handle it by using this COP modeling tools. So these tools also available in this modeling tab only. So these COPs type structures you can design it. So you can see, suppose some periodic observer, those things if you want to create some unopaque chamber type some environment. In that environment you want to simulate some antenna, how it will look like in that environment. Those observer part also you can do the designing it like here by using this cloud modeling tools. And next comes this suppose one brick you have created, in that edge you want to modify it little bit. So we are having one tool option like blend and chamfer edges also. This tool option you can edit in that radius, you have to just mention it and how much angle you want to put it. Like this part, from this brick we have created this thing, and here the chamfer width and the angle we have provided, and this structure become like this. So these are the some small toolkits what you have to tools. You have to understand how to use it. This is very important when you are doing designing from the scratch level. Here also you can see some transformer operation like Boolean operation. Another operation is there that is called transform operation. So here that brick is done. That brick we moved little bit. That is done by this translate, and the scale part if you use then it will little bit it will be larger, and smaller also you can do it. Rotation like 45-degree tilt or something you want to do, there you have to use this rotation. And next comes that cell operation part. Suppose you are creating some magnetic type structure. In that magnetic structure, this face you have to select first. After selecting the face, you have to go and select that cell operation. This is also available in modeling tab only. And next comes that loft operation. This is very important where you are going for means two structures are there. One is brick, another is cylinder. These two faces we have selected. So one is inside face, another is outside face. These two faces it should be assembled. So we have choose this loft operation. In that loft operation, we have given some kind of material we have used that is called aluminium. So mostly in a horn antenna design, if anyone is done, in that case we are using this loft operation. And next comes the bending part. In bending part, like some rod you have taken, that rod modification you want to do it, then bend it, you can use this option like this. And after that bending thing, you can show it like this. So this is mostly useful in kind of spiral antenna, those things you want to design. So in that case, this bending operation you can use it. So this variable textile antenna, if you want to do it, in that also this kind of design part you can use it. So port types already I have explained you in this port types, discrete port and waveguide port. These two type of ports are there. So if you are going for electric magnetic and this far field radiation calculation you want to have it, then in that waveguide port is mostly you have to connect it. And generally other terms like EM mode propagation knowledge if you want to have it, and current voltage calculation you want to do it in that case discrete port type. So these are the thing S parameter calculation. So here we have taken one example how we implant this discrete port. You can see it. We have designed one mic line in that we have putting one discrete port here. And in this discrete set post, we have mentioned S parameter and this impedance value as we have taken as 50 ohm. So this is one example of discrete port. So this is another example in that we have choose means in that example only you have choose different edges like this, and by using the peak edge option, and after peak edge and a face option when we choose, and we have given that we put the discrete face port like this. And next comes that port definition like in for closed structures. So this is one view of horn antenna. In the horn antenna backside, one port you want to connect it. There you have to select this like two edges you have to select it, and after that in between that point you have to select. Once you select it, face will be selected. Once face is selected, you can do it. By choosing that way also you can do it. And another way is like you can come to this home tab option here. Also BBA macro one option is there. If you go to this BBA macro option in solver part, you can see one port option is here. So in that port option also you can do it. Like that somewhere one port you have to put it. In that case you can do it from there. Suppose 4, 5, 6, 7 ports are there. You want to do it. So there you are using this BBA macro option. In that BBA macro option we are going to solver, and after solver port section we are choosing, and from there allowing overlapping waveguide ports you are selecting. Once you are selecting like that, it will show you like this one window. In this window you can see all those waveguide port, all those things we have explained. So that way also you can do it. And if you go for 6, 7 port design, then you can choose this BBA macro solver option also, no problem in that. So once the structure part is done, we are going for result calculation. In that result calculation, you can see I have designed one MIMO antenna here. So in this MIMO antenna already have designed. So this is the navigation tree I was talking about. So what kind of components are used? So I first design one unit cell. So that unit cell only I copied and mirrored it in another way. So this almost everything is done. And what kind of materials are used here, you can see it. So results part is like once you do go for simulation and you select it here and start simulation, and after the simulation part is done, all these results it will be saved. Like here ports are, how many ports I have used in this design, around 4 ports I have used. And this OND results, all those things you can verify it by using it here. Like S parameter, all results you can see how it's coming, like S11 and this one. So these things are mentioned here. And this far field results you can see it here, how it will look like. So this is the 3D view, and this is the 1D view. If you want, you can take it from here. So these are the thing. Suppose you are working in MIMO, their array part you are working there array factor option is very important. Little bit tilt if you want 15, 45, 60 like that, 15 to 15 degree you want, there you have to give instruction from here array factor. And those results you can check it by choosing this far field result option. In far field result option you can select this part, and you have to go this all setting option. And suppose you want to change some step width also, you can change it here. Like here 5 is there, you have to mention it. 1 also you can mention it. And MIMO, all those directive gain, all those things are explained here. Like this you can see. So all those part is explained. And here you can see this as we have taken for 1D polar port. So this is the directivity part, plot mode, everything. So like this far field is option is there. So we'll go a little bit deeper in this, no problem. So just overall lookout I am doing in this section, what you can do. So this is the result part what I have explained you. You can go for template based testing also. The 1D offline what you are getting, and this curve my curve, everything here perfectly explained. So in electric field, magnetic field, those animated part also, effect also, you can put it in your presentation, no problem. So those things you can verify it here. So one page antenna we have created. In that page antenna, all those part what I have explained, those things we are testing. So in post processing, how a result can be verified, those things are there. Next comes the parameters we type. So for choosing that parameters, we go on to results and we have select this table as like this. So these are the things what is there in this. Now we'll jump into optimizer part. Optimizer part is very important when you go for several ports are you are having, and you have to give particularly one setting is like uh, here you come, and in this home you choose, and in this all portraits are there. Suppose you want to uh, simulate it in one port only, those things also you can do it. After that, you can give instruction option. Here you can select that port one only I have to do it, and rest thing I have to isolate. You can see that in that all S parameter result you will get related to port one only. So some structures are bigger. In that bigger structures, you have to use some acceleration token also. In acceleration token, it will improvise your simulation speed, and it will give you result in certain time. So that is part there in this acceleration token. And this MIMO antenna part, suppose once you've done the antenna part designing, and you suppose you are having one mobile CAD file, that mobile CAD file you have to put this antenna. So you can see that case everything we have got it from CAD designing, CAD designers, and in that we implemented this thing. So for implementing that part, you have to go for this import export. In that 3D file you can import it as CAD file. Here you can see CATIA, SolidWorks, those things are mentioned. You can import by like this, and after that, that antenna what you have done, that part you have to press it here. So once that thing is done, you can jump it like here like this. So directly you can come and can do the rest. So this is one example of a mobile phone MIMO antenna. Here you can show, here you can see that workflow how you are doing. So I mentioned you about that CAD file what we have taken, and in that we have integrated one antenna, and that integrated antenna we have put it in the simulation. And this simulation done, we have gone through that antenna matching part, and bandwidth potential we have measured, and all those far field results we have taken from there, and this MIMO analysis we have done. So here we can see I mentioned you integral equation for extremely this last structures we are doing for this integral equation solvers we are using. So this characteristic mode analysis you can see, and this comes that when you gone for this case integrated with antenna part, there you have to select this mesh analysis also. In this mesh analysis, you have to verify how many cells it will be there. So it will depend upon how many mesh cells it will create. So on the depend of mesh cells only, that simulation will take more time. If you are having more mesh cells, then it will take more time to simulate it. So if you want to do it very quickly, then that part also you can do it like this. So once that mesh view you created, that structure what I have shown there, same that mesh view you can see it here. So it will be look like this. And once you create that integrated equation solver, in that you have to select the CMA options. After that, this model tracking, these options you have to give it, and at what frequency you want to verify that 0.8 gigahertz or anything, that thing you have to mention it. After the simulation part is done, you can see and verify all those results what is there in CST. So as per your mentioned key, this mode is every mode that what results it will look like. So you can see the surface current density, everything, those things are mentioned here in this diagram. And this corrections mode analysis also. So these all far field radius in mode 1, 2, and 2, both options we have chosen here. And those patterns what we are watching, those 3D patterns are completely visible. And if you go for a little bit deeply this parametric study also, you can go for this parametric sweep. Like here only this option is there. So whenever you go to home section, here you can see just now this simulation is running. So if you go for this parametric sweep, one option is here. If you select that parametric sweep options, it will give you to take you to window like this. In that window, suppose you have created one MIMO antenna, that sequential wise you have to present there what sequence it is there. So all those sequence from 80 to 82 we have taken, and 5 samples around we have taken. In that result what you have mentioned, after that we are running that part and we are getting result like this. So all those results parametric wise also study also you can do it. And suppose you are using any dielectric also in that structure, just you have to go and check in that backfield also, background also. And after that background part is done, you can get the result like this in sprites. So when this antenna part is done, this integration is done, there you have to go to this parameter list. In this parameter list, anything you want to change it, then you can change it by using this parametric list. No problem in that. So these are the things what is there in MIMO antenna. So MIMO antenna is like uh, very big topic, but we have I have collected every data what is needed for you in a PPT like format, so it will be easier for you to understand. So this discrete port what I have mentioned, we have selected one discrete port here. When that antenna will be integrated with your CAD design file, at that time you have to if you want to run the simulation, you have to put one discrete port. So that discrete port we have chosen here in that part. So you can see this discrete port part we have done it. And after that the integration is done, then we can see the total view how it will look like with CAD file. With CAD file now it look like antenna part is here and to connected here and it is completely integrated. Once that integrated part is done, you go to your navigation tree. There you can see in your component section all will be listed. So these things will be listed. So this is the part you can easily you can handle by using this CST Studio Shoot. And next comes that CST Studio Shoot, how it will look like from align mode. Align mode you can see before that antenna structure is little bit up. You can rotate it and you can put that thing inside that case, no problem. And we have done some options like tab, shift tab options we have choose. In that we have done this part like this. And once this part is done, you can see those results what we have got. So again we have gone through this mesh view and result part like time domain solver you are used. Accuracy we have taken around -3 and results we got like this. In that antenna matching and bandwidth filtering, when you go for this result template options, like here in CST, when you go for this like MIMO you choose, in that result template option is there. Here you have to go this far field antenna property. In this far field antenna property, you can see all those options. You can see max field and free field, all those things are there. And you can choose it from there. Otherwise, you can go to this far field result also. In this, all those TRP value, MIMO, and those this part are mentioned. And you have to browse that monitor also. You can go through it. And simulation, this field monitor option also there. Here also you can come it and do that thing like far field RCS and that measured frequency at what you want to verify it. I think you have to explain it here. Once that apply you do it, then that result it will show you in this navigation tree. So like this you can do the task, no problem. So this is the antenna matching board loop accuracy and the results what we have got from that like 1D results we have got it. In the 1D results you can see both phase return less everything. And suppose you want to add something in that thing like some circuit level, some modification you want to do inside mobile, that part also you can do it by using this CST schematic. So here you can see different kind of topologies, what things are there. So as per your requirement, you can verify the topology also. So in macros also one option is there in matching circuit. If you go in matching circuit, it will show you 3 options like obtaining layer, mini match, and beta match. So if you go for mini match, you can do like this. But nowadays people are using obtaining layers also. This is a add-on module. That module you should have it installed it in your system. So that one is compatible with the CST Studio Shoot. So these things you can do it from by using that. So here you can see that LC circuit we have designed it same using that CST schematic. We have put in that antenna structure like this with case based with antenna structure like this, and in that external port and one resistor conductor we have delete, and you can see that view how it will look like. So all those things, and same thing Once that schematic part you have done it, you can go and select that task. In that task, you can go for this S parameter result. And S parameter result, once you select it, it will show you that frequency at what you want to measure it. So CST file, if you want to simulate it, use it. You can use it. If you are having Spice also, you want to export that thing, you can use that Spice export option also. No problem in that. Once you given your task, you can go for that update part. Once you click on that update part, you will get S parameter result like this. So MIMO antenna with case like total whole mobile structure, you will get the result. Those result it will be see, you can verify it. It will be like 0.8006 gigahertz, and these things also you can do it. Like S parameter, you can go for this AC combined result also. This AC combined result also you can verify. These things are already meshed. In that, what we are doing, whole model we are putting as a block. That block, you can see it here how it is done. And next comes that antenna combined result options. Like so many far field options results, we have got it in different frequency level. Those results you want to combine it. So how to combine it? So those options also here in this. So you have to go to that post processing part. In this post processing, if you go here, one option is the combined results also. In this combined results, you can see all those tasks are there. Just you have to give it here amplitude and passive at what level you want it, and after that you can go for it, no problem. So this is the far field result reduction part. And next comes that MIMO. So as you know, MIMO means multiple input, multiple output. So this is the one over the performance MIMO analysis we have done it. So created one environment. In that environment, we have taken some files from online and we have put in this MIMO antenna. We are verifying these results from there. So if you've gone through wireless propagation model, we are using relay fading method. So these all things what we are doing, those things can be put in Python script also, no problem. Those Python script model you can utilize in MATLAB also and other application also where you want to go further study, you want to further go and study this thing. So once that part is done, you can go for this total radiated power also. Again, you have to come to this template based post processing. In the template based post processing, when you choose this far field antenna property, it will show you this uh, thing. So just template based post processing is there. So when you choose the template based processing, it will show you this far field result one options. Once you click on that far field result options, it will show you the total radiated power. So these two windows it will pop up. In that in window pop up, then you can see all those variable designs you can put it, no problem in that. So these are the things what is there in this MIMO antenna. So more accurately if you want to do, so again you have to go in this template based post processing only and you have to select these modules like this and you have to go further and further. So you can see in template-based processing what options we have chosen. One power pattern we want to view it, and another electric field also, and this bandwidth potentials also. So all options once selected, you go for this evaluate all options. Once you put evaluate all options, it will show you all results in this navigation tree. So all those results you can verify it in that navigation tree 1D results. So these are the things what is there in MIMO analysis. Just like 1D results, you can go for other like mean effective gain also, those things also, and those things will be saved in 3D results in far field options. So these are the things what is there. So far field results and these things. So these things comes under this MIMO part. Now we'll little bit we'll go for this uh, metamaterial part. So can anyone tell me what is metamaterial? Hello? Hello, sir? Hello, sir?
Yes, sir.
Can anyone explain me what is metamaterial? Now I should start from my side only. No problem.
Any
Okay, so metamaterial, what is not natural material like artificial material where? Okay, sir, I will start. No problem.
queries?
So
Any
up
response
to
from the
MIMO any
participant?
up to MIMO any query people are having. Now we'll jump into metamaterial part. Yeah, up to this mark like MIMO antenna design, if people are having any questions, then you can ask me.
You can proceed, sir.
Okay. So metamaterial part is like first we have to set it what is metamaterial, those things. So now we'll jump into, I have created one presentation PPT slide for you for this metamaterial. So you can get it like metamaterial is what? What is our natural way those properties, what you will not find it. Those properties will get it by creating these artificially built metamaterials. So metamaterials are like what kind of property you are studying from there. So you can see this cloaking and negative index, all those parameters we are handling. So in that metamaterial energy band curve structure is very important. So all those things are explained through what kind of material. Sometimes you will not find material as per your requirement. So those plot, depression, everything, dispersion, everything, you have to put it like this. When I explained about CST Studio Shoot, at that time I go to that material library section. In that material library, when you go for creating new material, there you have to give that epsilon, mu, and all those dispersion, all those values like. And once you give in that dispersion value, you will get this. All those things, you'll details, you'll get it from that energy band tag. So mostly people working in material synthesis, they are going for this type of things. So where this metamaterial mostly used, so you can see so different type of metamaterials we are using in EBG, MC, and low profile antenna also, and bulk left-handed materials also, and transmission line materials also there. So these are the type different materials. So as per material classification, we are seeing that is we given four things like plasma level, how its graph will be look like. So all relative conductivity, dielectric, those things you can verify it. So this is very good graph for demonstrating that thing. So all this LH material will be characterized by their negative reflect index. So you can see it, those who are getting value not in backward propagation also happening, those things we can put it. So these are the different metamaterials and those methods. And metamaterial classification are based on this band gap. So I mentioned you that energy band gap. So we have done it like this. Those to go a little bit further studies, those values will be like that. So this is the reaction and velocity part. So this is the zero. And now we'll go for that workflow for metamaterial simulation. So if you want to design any metamaterial, so first you have to choose this design one unit cell first. So in that unit cell, how to do the designing part and dispersion diagram and phase reflection, those things you have to get it. If you are getting proper result, then you can go for that metamaterial part. So mostly we are using in metamaterial this eigen mode solvers. Earlier I mentioned you that a time domain solver and those things, integral equations also solver I explained you. So in this metamaterial we are using this eigen mode solver. In eigen mode solver, what kind of mesh cells we are creating it. So those are like two types like tetrahedral and hexahedral. And material while creating that structure is we are using what kind of material. Those materials also I have explained. So with this, we are giving simple boundary condition, and after that boundary condition only we can get this energy band graph like this. So you can see all those things. And transient solver, if you are using time domain solver only, in that fit technique we are using. So fit technique also you can verify it. Suppose little bit complicated big structures you are designing, in that you are using. And some transmission line filter like some unit cell only you are going, then in that narrow band result if you want, then you have to go for this frequency domain solver. So all crowd size structure, in that we have put in this locate port also. These all things are used in cavity filters. So simple workflow, what you have to go through if you are designing one metamaterial, then you have to go to that microwave RF section, and in that you have to choose these periodic structures. In that periodic structure, suppose you are going for frequency selective surface, then you choose frequency selective. Otherwise, you're going for metamaterial full structure design, you can go for that. So what is the outline, you will go for it. So these are the application examples what you are doing. So these things are there. So once the unit cell is designed, so you can see all those diagram like boundary condition we have put it. In that boundary conditions, when you go in that X per Y, what things you have to mention it. And again, you have to go to that parameter sweep also. sequence wise you have to mention key in X direction it will be how much angle it will be verified in that 90, 180, those things you have to mention in sequence 2 in Y direction, different direction you have to mention. After that, you can see those things through that graph analysis. And when you give port in different types, you can get the results like this. So one surface current distribution, we have done it through 3 gigahertz. So that results what you have got it, the results I am showing you here. So these are the results in high impedance cell surface like this. So one by one, those results, behavior, all those things you can see in 3D pattern also. So these are the things what is there in this thing. So I have created one meta material already because here some time restriction is there. So I have created one meta material structure for you antenna one unit cell just now. So here you can see what kind of components we are used. So in this all this period ground ring, these things are there. So I went to this modeling and here only I created it. And after that I got S11 result like this and this far field result. So this is 1D polar plot and 3D polar plot in this. And here we have field if you go through and you can see it by doing it like this. So these are the component like metamaterial, what is there. So metamaterial, if you want, I can share you this workflow, no problem. And if further anything you are having like periodic boundary condition and those things also you can go through help section and you can study further. So some things we have done it, and if further any complete things is there that is like different frequency level you want to adjust and different things you want to verify, those things also we can do it. So sir, any metamaterial kind of thing is there? So just let me go through questions. If they are asking anything, then I will go a little bit more deeply.
Hello.
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 Hello. Sir. Am I audible, sir?
Yes, sir.
So
Sir, I have a question, sir.
Okay, sir.
Sir, you have shown that frequency selective surfaces, but that is a metamaterial antenna you have shown. But I want to ask a question related to frequency selective surface.
Okay, sir.
Sir, while designing frequency selective surface, we design a single unit cell. Hello. Sir, are you able to hear me?
Sir, I can able to hear you. Tell me.
Okay.
So you have chosen this FSS material in that unit cell you have designed?
Yeah, I have designed it. But now I want to make an array of 3 cross 3 of that unit cell.
Okay.
And now I want to simulate it and then I want to make it conformal.
Okay. Conformal array antenna designing that part.
Yeah.
Means
Not antenna, sir. Not antenna. Only that
surface you want to do it. So
yes.
In that just you have to select like this, sir. And wait 1 second. So for that array part, what you mentioned, sir, for that you have to go to the simulation project, sir. One that unit cell is designed, done like that. I have done one metamaterial antenna. This part is done.
Yes, sir.
So just like you have to go to this home and you have to click on this simulation object, sir, project. In this array task one option is coming.
Okay.
Okay, sir. You have to choose this array task. Just wait 1 second.
I think this array task is not available in 2024.
No, sir. It's available in every option. It is available, sir. I am showing you this like phaser antenna also. This unit cell I have created, sir. Here, like you mentioned about page antenna. Same, we are creating this array part. Let me show you. See, sir, this array part what I mentioned you. So just you go to this simulation project. In the simulation project, you have select array task. Okay.
Okay.
So once you go to array task, there you can show this all detailed specification. One option will pop up, sir.
Okay.
Okay. in that different shapes you can choose it, like octagon, hexagon, diamond, what kind of shape you want. Okay. So one that
Okay.
shape, then that elements, how many elements you want. You mentioned 3 cross 3 you want. You mentioned
Okay.
that.
Okay.
So
Okay.
you have to put your angle also there, how many angles you want, and after that it will show you one
Yes, sir.
thing like one shape type structure. It will show you like this. In that,
Okay.
in between each element, how much space you want. That space also
Okay.
you have to mention it here, and that
Yeah.
grid
Yeah.
angle is for that different cells, how much that grid angle should be. And once that part is done, it will go for this array task setup, sir. In that array excitation pattern, one option it will be there when you go for designing. In that array one tab, it will be there like this, and in that array tab you can go for this array excitation pattern. So different kind of patterns are there, but we have chosen here only Taylor pattern. In the Taylor
Okay.
pattern, at a side lobe what you will get it. So you choose a separate thing, but in separate antenna part we are choosing like this, sir, array task part. So in this array
Oh,
task part we are choosing the side lobe separation should be like this, and we have chosen this excitation pattern as Taylor pattern, and that view will create it. So after that, from that unit cell, we are going for this create unit cell option, sir. Okay, na, sir. So once
okay.
that unit cell part is done, we are creating this create unit cell simulation project option,
Okay.
selecting. So once you create that unit cell, there you have to mention key from theta degree angle and 5 degree angle. 5 degree angle means what your azimuthal and spherical, it will be how much. That angle and the step width, all those things you have to mention it. Here we have taken 0 to 45 degrees. Somewhere we
45.
have taken minus 180 to 180 also. Once that part is done, you can go for this far field monitor options. Like in monitor section, I told shown you, sir. Again, you have to go monitor section. There in that array task option, again you have to come to this boundaries. In that boundaries, if you are choosing for tangential electrical component, then you have to choose like this Z mean direction, only this part you have to done. Suppose you are going for flocket port analysis, then you have to choose this flocket boundary option. In that boundary option, again you have to mention it, how much it will be verified and how many modes you want. Like 19 modes we have explained it here, and we have to take on that polarization independent of that scale angle phi. Already you have seen the 0 to 45 degree you have taken, and another minus 180 to 180 you have taken. So that
Okay.
thing part we have put it here tick. So this is the array task, that boundary condition when you choose, and that pocket port analysis when you do. And after that we are going for this full array simulation project. In that we are explaining everything positively, and excitation part we are explaining this port wise port, how much it will be amplitude, phase shift it will be there. So suppose you are creating 3 cross 3. In that 3 cross 3, you will use around some ports, na, sir. That port thing you have to give that option selection. You have to do it like this. You have to come to this excitation selection. There you have to shoot this amplitude, phase shift. You have to mention it. Once that part is done, after that only you can go for total simulation. You got an
Okay.
idea, na, sir? What I'm telling
Yes,
you?
sir. Yes, sir. Yes, sir.
Yeah, navigation tree only, this task one bar will come up. In that array one option will come up. In that unit cell one, what you have done metamaterial, that thing, and another from that unit cell metamaterial, that full array what you have created, like this one
Okay.
option will, and that update part you will do it. And next comes that array task simulation, same to same, that what I mentioned you can do further, no problem.
Then how the conformal part will be done, sir?
Conformal part, I am having another workflow, sir. I will send it. So up to this part means up to whole workflow, you can design it by using like this. When
Yes,
it
sir.
comes
Yes,
to
sir.
conformal part, there you have to go to this parameter list as per your requirement. You have to change that a little bit, beam sharing, those things. You have to little bit. You have to change it. Suppose you are using this part. So I
Okay.
have done one conformal array antenna part. From that, I am telling you. So your is like metamaterial you mentioned. So for that, I have to create one workflow for that. And
Okay.
if you need, you can go for that help section also. If you come here and if you go for this help section also,
Sir, can you please share that PDF,
which PDFs?
sir, which you are
Sir,
showing right now?
that workflow I can share you, sir. Some part of that PDF. Those are like, actually confidential PDF, sir.
Okay,
That
sir.
is the
It's
point.
okay. It's okay, sir. It's okay, sir.
Some part of it I will share with you, sir. No problem.
Okay, sir. Okay. Thank you.
So this is the conformal thing you can do it for crop sir, and conformal other part from metamaterial point of view, I will share the details with you, sir. So
Yes,
up
sir.
to this full metamaterial part, how to do it, that part somewhat you got an understanding, I hope.
Yes, sir. Yes, sir.
So MIMO and this metamaterial part we have gone through today. So thing is that any other person having any other questions, sir? Any questions, sir, from your side? Any other questions?
Any questions and any queries from the participant side?
So just now we have included this one another application, sir, in CST. That is called MCAD. Earlier, this application you never heard about, I think. So MCAD one application just now we included. If you are going for any base station antenna designing, also nowadays this 5G things in market is there. So those
Sir,
files we have designed.
sir, how to assign any optical material in terahertz frequency?
Optical material.
Optical
Sir.
material.
Tell.
How to
Optical
assign?
materials.
Yes, sir.
How to assign optical material?
Just like in terahertz frequency.
Oh, okay. New terahertz frequency, sir.
Yes, sir. Yes, sir.
So optical parts, sir, for that we are having this project template you have to go. You can choose this optical application part, sir.
Yes,
In
sir.
that, if you're working dielectric, choose it. And here different options are there, like solar cells. If you're working, you can mention solar cells also, and photonic band gap structure also. I have taken one example, optical
Simple
waveguide.
antenna. Go for simple antenna, sir. Terahertz antenna.
What, sir? What antenna?
Terahertz antenna.
Terahertz antenna. So terahertz antenna is like here, sir. You have to come here, and after that, when you go for this, anything you design, you choose this and go for time domain. In that, here you have to mention that all those dimension part you already know, but here terahertz, that frequency level you have to mention it, sir. And after that mention part is done, when choosing that optical material, you have to come to here this material library, and suppose your material is not listed here, that material what you want. You are following some research papers, sir, for designing that
SiO2.
SiO2. So SiO2 you have to type it here. Just 1 second, sir. It's getting little bit slow. So silicon loss free is there, silicon lossy is there, sir. So once you click on that silicon lossy or loss free, you can see those attribute part in down there in this section. So if you're following any Pozar book or anything like microwave related, in that if you go to back of that book, in that book all those material and material details it will be listed, and you are referring any research paper, that material what I mentioned, you mentioned SiO2. If that material, all those epsilon mu, it's okay with this material what's showing here, then okay, you can choose this material, no problem. Suppose that material is not listed as per your required, means epsilon mu, all those values, it's not matching what is needed in CST. So you can go for this new edit options. In that new material, you can select. In that new material, you can mention that new material name is just silicon dioxide or like this. And here you can mention that epsilon and mu value. And next comes that conductivity part and dispersion part. All those part here, dispersion model is there. Here you can choose by all those option is there. Gyrotropic also. Suppose some user defined selective list you want to take it, for that also you can choose it like this for dielectric. So after this, that material will be created for you. So that thermal response also here. So here you can go for thermal options also. In that thermal conductivity, everything is there. Suppose this is PTC or this is anisotropic. the specific heat, absorption, all those things you have to put it, sir. If that silicon dioxide Si2 option is not available. But from my use point of view, I am telling you, if you go to this material library, just you click it here, silicon. Here you will get all those two things, both lassi and lassi free. Just wait 1 second. So if those characters it's not matching with your research paper, what you are referring, you can go and create one new material for you. No problem in that, sir. Got an idea, sir, what I am telling you?
Okay,
Hello?
sir. Okay, sir. And how to do the bias voltage?
Bias voltage part, you can do it, sir. Here only. So these parts are here, you can explain, no problem. Conductivity part.
Bias
And
voltage
bias voltage,
in
for
terahertz.
that I have to bias voltage in terahertz. Could you give me that research paper, sir, so that I can send you what you can do in CST specific for that research paper?
Yes, sir. I will send.
Okay, okay. So terahertz is nowadays everyone working mostly. So material part you can do it, sir, like this by choosing this material library, otherwise new edit. So some other things you mentioned, ki bias voltage part you want to go through it. You want to see ki how that thing we can verify it by CST. That part I can send you, sir, coming days, no problem.
Okay.
Oh, okay, sir. Hello.
Any other queries on the participant side?
Hello.
Hello.
Sir, one silly question maybe. Sir, actually, I want to learn that how to project a planar surface on a conical surface. Is it possible right now to show that
Planar surface and conical surface, sir.
one
So
planar surface, like I have designed a FSS, let's suppose, of square patches are there. Then I have to project it on a conical surface, like the radome of a plane.
okay, so for that we are having actually one workflow. 1 second. Actually, that part is not here. Otherwise, I could have explained to you. So large unit that. Okay. That part can be done, sir. No problem. What you have mentioned.
So
In
you just
conical surface also
you
can
can
do.
just brief me. I have that CST in my college and I can do it.
Okay. Something left. So what do you want to actually questions you asked that plasmonic periodic arrays, na? Just I'm going through where that part is there. Yeah. So this is the unit cell you are talking about, na? this
Yes, sir.
uh,
Frequency selected surfaces and locate.
um, okay, one second. This is the plane wave view of planar wave. PGM. So what you can do, sir, you can uh, share me that question what you asked. I can share you that total thing what you have mentioned. Ki conical part you want to change it, na? That part.
Actually, I want to project something on a conical surface, like how the designs are designed on a cloth when the cloth is in conformal shape.
That part you can do it, sir. But thing is that ki that kind of thing what you want to know right now. That thing, Redomi thing you mentioned, those things on that one unit cell you put it. After that, some mirror you option by choosing that mirror option, you can create so many elements like that surrounding that Redomi. That part I
Yes.
have done from my side. And
Okay.
another is there ki suppose you have created one arithmetic in that you can little bit modify it in XY plane. After that, you paste that part like 1 1 1 1 1 1 like that XY Z direction, and up to some mark you can put it. In that, what will happen? That mark will be totally identified in a circular way.
Okay.
That conical will be there, but in that circular way that will be represent like 1 1 1 1. It will be radius wise. That spacing also you have to dimension also you can measure it there. One workflow I am having, but right now I don't have in this thing, means I did not prepare for that thing. So if you want, I can share you those workflow, no problem. Like what I
Okay.
mentioned to you in conical surface, how to go for this surface plasmonic those parts.
Okay, sir. Sir, can I share my mail ID in the chat box?
You can share it, no problem.
Okay, sir. Okay.
Okay, so let me share my mail ID also. If you people are means any questions further you want to ask, you can share it with me.
So there are two questions in the chat box. Is this CST tool freely available? And any YouTube
This
link to learn this tool from starting?
actually, sir, this CST what you are right now saw those things. If you are having mesh cells up to 1 lakh, you can do it by using this CST Learning Edition. For that Learning Edition, you have to go there in Google. Also, you can type it CST Learning Edition, and it will show you this student CST Studio Suite Learning Edition. And after you have created one Dassault account, you can go and download that part and you can use your system, no problem. It will be completely learning edition point of view. So some boundary it will be there, like up to 1 lakh cells you can't, or above 1 lakh cells you can't use it, like simulation point of view. So below 1 lakh cells, if you created anything, then that part you can use it by using this CD or Studio Shoot Learning Edition.
Thank you, sir.
So this is the thing, and other tutorials you asked. So once you go for that downloading this learning part, so you can go for this Studio Shoot tutorial also. Here you can go for all tutorial what you needed to learn. Like
I want to create hybrid beamforming antenna. Will it be okay for this?
that is no problem, sir. Hybrid beamforming part you can do it. Antenna
Thank
part
you,
also.
sir.
And I think if you want to further, you people are currently in your lab using CST Studio Shoot. You are having? Hello?
Yes, sir.
Your people that lab of in your lab you are using currently CST Studio Shoot?
That is question being asked by Hina Singh actually in the chat box.
Okay.
No,
So,
she said no.
So we are using
Oh.
at Bits Pilani.
Okay. So 1 second. This is the question. Can you send link to use it? That is one. and I am transferring this call to practical extension. Please share PDF and 7 short quiz. CST tool freely available and any link to learn to this spec. So I mentioned this part, sir. CST tool is available, CST Learning Edition. You can use it, no problem. And next comes that, this is your mail ID you mentioned, no? Okay. Okay.
Yes, sir.
So CST Learning Edition, you can download it. You can use it there, and tutorials also available. So YouTube also, those things you want, you can do it. And I want to create hybrid beamforming antenna. Will it be okay for this? So Learning Edition, you can't go for this kind of antenna development. So if you are having like a CST license, research license, there you can go for this hybrid beamforming type of antenna design. Is that okay, sir? So for that you need one CST research license, sir.
Okay, sir. Thank you.
Okay.
Any other queries from the participants? Thank you, Vivek, sir.
Okay, sir.
On the behalf of the participants, organizing committee, and from MIT Group of Institutes, I extend my heartfelt gratitude to Vivek Bakshi, sir, Senior Application Engineer, Jyoti Microsystem Private Limited. Sir has very well explained the multidimensional features of CST software. Thank you once again, sir, for your valuable time and contribution to this FDP. Thank you very much, sir.
Okay. Thank you so much, sir, for giving me this opportunity. Thank you, sir. Then okay, sir. Shall I leave or is that okay?
Yes, sir. You can leave, sir, if you want.
Thank you, sir. Thank you. Thank you, sir.
Moving ahead to our FDP program, we have honored to have with us Dr. Shweta Amit, research scientist and founder, Smart Beam Resonatics. Madam, on the behalf of MIT Group of Institutes, I welcome you on this 6th-day ATAL FDP program. To formally introduce you, I invite Dr. Rashmi Pant. Over to you, madam.
Good evening and warm welcome to all. It gives me great pleasure to introduce our expert speaker for today's session, Dr. Shweta Amit. Dr. Shweta Amit is seasoned and dynamic professional with over 17 years of comprehensive experience across academia, industry, and research, a specialization in RF, antenna, and metamaterial design and development. She is the founder and research scientist at SmartBeam Resonatics, a registered MSME research initiative focused on integrating artificial intelligence, quantum communication, metamaterials, and next generation antenna system. Through SmartBeam Resonatics, Dr. Amit envisions pioneering innovation in smart antennas, RIS-based systems, and intelligent beamforming using advanced simulation and algorithmic design. She serves as consultant in RF and antenna engineering, actively engaging with clients in aerospace and defense and commercial sectors to deliver cutting-edge solutions. She is currently consulting for Entapal Technologies Private Limited and Josh Aerospace Private Limited, Bangalore. Dr. Amit has deep expertise in the design and simulation of high-frequency antennas and RF components using leading tools such as ANSYS HFSS, CST Studio Suite, FEKO Twin Builder, and EMI EMC analysis. She has successfully executed mission-critical projects for the Indian Navy and Indian Army under the Defense India Startup Challenge, organized by the Defense Innovation Organization. She was the winner of two prestigious DISC challenges in 2021 and 2022 for her pioneering work on liquid antennas and conformal antennas, executed in collaboration with Goa Shipyard Limited and Bharat Electronics Limited. She was felicitated for these innovations by the Honorable Defense Minister Sri Rajnath Singh. She is also a certified NSS professional, a senior IEEE member, and gold medalist in her MTech program from RVCE. We are honored to have her share her expertise with us today. Please join me in warmly welcoming Dr. Shweta Amit to deliver expert session. Welcome, ma'am. Over
Thank
to
you.
you, ma'am.
Thank you. Thank you so much, ma'am. Thank you. A very good evening to everyone.
Good
I'm
evening, ma'am.
I'm sure all would be exhausted with the FDP, and since this is the last session, I will
Yes,
try
ma'am.
to make it a bit interesting and everything. So today's talk will mostly be on the journey of what has happened to the evolution of antennas throughout. How do we manage this design of antenna in terms of beamforming? Why is it necessary? And then, so since everything is getting smart and AI is being put, so and we also know that 6G is completely AI assisted now. So let's see what should we be prepared for the next generation if 6G comes up. So how exactly can I use the power of AI to probably have a efficient way of catering these wireless communication, right from a simple antenna design to the way it beamforms, to how exactly can I use these AI tools so that even if I move with high frequency, that is sub-terahertz or terahertz also, I still can survive. We will just see what are the challenges, how do we face, what are the different ways to mitigate these things. So this is how the flow will go. Just give me a minute to share the screen. Hope the screen is visible. Yeah.
Yes.
Yes. Okay. Yeah. So as we see, so too many terminologies are there here. So right from how did this wireless network get into global communication? We all know that, how this happened. And moving in a faster speed with respect to the generations of 1G, 2G, 3G, 4G, and 5G presently having a amazing improved speed and latency. Well, 6G completely has a new vision towards having its own intelligence, probably having its own adaptivity, and of course, ultra fast networks. This is what are we looking into it. So one thing comes here is, though everything looks nice with respect to having it intelligent, adaptive, and ultra fast and everything. So how do we cater into the other things which are at flaw now? The moment I say I move into 5G, 6G, my NR, FR1, FR2 frequencies. So how is what are the other challenges right from physical layer, MAC layer, network layer? What is happening? How are we getting into trouble? So if we are able to recognize that paves as a way to understand what more should I do to realize that I can do a better work. So first thing is, antenna plays a very important role, right from understanding the signal propagation, coverage, and actually energy efficiency also. So AI now integrating with antenna design, which would help me in beamforming. So how does it have to do it in a dynamic way? And it has to be real time. And of course, having to make it smart also. So our agenda today for the next 1.5 hours will be as to understand what is beamforming and what kind of these AI methods which are already existing could be catered in these antenna and beamforming systems, and what are all the design considerations should I take. So I have mostly been working on antennas itself. So if I consider an antenna, so far, whatever frequency I've been working in microwaves, so what is the material I have used? What are the challenges I have faced? What is it that I have seen? So is this the same challenge which is existing when I move into the higher frequency also? Even in a millimeter wave, let alone sub-terahertz. So what are all the design consideration I have to be very aware of? And then comes what is smart beamforming applications and what are the challenges and how should I be ready for my next way of research. So antenna, this slide is just a simple slide which we already know it. So right from having So the definition of antenna, as IEEE says, a triple R's, something which radiates, receives radio waves. Fine. Okay. The key parameters is for me to having known at what frequency I need to operate, for what application it is. So satellite communication falls under certain frequency. We know why it has to be in that frequency only. Why can't I use any other frequency? And why did we altogether move into millimeter wave? Though I had certain bands in my CNX bands. So why did we go into millimeter wave? So what determines me the power of having to choose the frequency also? And then comes is the gain and the radiation pattern. So radiation pattern with respect to spatial distribution, now I have to be very careful with respect to right from calculating how much would be the power intensity, radiation intensity, what is the beam area, what kind of polarization should I have to give. So it starts from basics when I plan about any antenna, of course. And then comes, no matter how much ideal I talk about or design it in my simulation tools also, due to this power loss of talking about directivity versus gain. So in ideal scenario, I know how to calculate directivity. I know how to do, but the moment I put it on a system where it has to sit, either it is a cell phone, it is a base station or a satellite itself. So the moment I put on top of it, what gets knocked out? So how should I be careful? So one or two challenges where I came across was when we were doing a defense project for naval warships, wherein we had to reduce the RCS. So we designed, it was basically based on liquid antennas. Standalone antenna was a wonderful way to demonstrate and show everything. The moment I put it on such big mast of the ship itself, too many things came into picture. So how do I understand that? So when I talk about power loss, are there any other absorbing material right beside me to take care? I mean, that is, metal is one part. How about, we are talking about everything being connected to internet, right? IoT for everything. So even body area network, if I'm talking. So if I'm designing any antennas for my own, I mean, near the body. So how exactly does the radiation affect us? And at the same time, how much is my body or the human body affecting the antenna system itself? So it goes, both goes hand in hand. So how should I take care of it? It's no more about designing an antenna standalone. It's all about how do I integrate it. So fortunately, with the power of digital twin, in every other tool, right from ANSYS, so every other simulation tool, what I have come across. So this gives me a complete usage of trying out multi-physics. So that's where, and design an antenna as a component, put it on a system, and then analyze what is happening. So as simple as probably designing an antenna for my smartwatch, and then looking into the other ways of how exactly the moment it bends, what happens, it conforms, what happens. So one of the other project which we did for defense in 2022 was to design a conformal antenna for Indian Army. So wherein we had quite good challenges there. So we had to design these conformal antenna on the helmet itself, on a bulletproof helmet. And these antenna also had to be bulletproof. So what do we do? How do we cater to it? So here comes the real-time challenges. I mean, 13 years of my experience in academics and moving to industry have now given me an understanding that yes, as a faculty, we know the basics very well. We know how to design a standalone product very well. Trust me, we know it. The moment it comes into the industry perspective, when I have to integrate it into something, and we have to test it for the Penta 5 standard, JSS Penta 5, in terms of MIL standards, part of it. So many things comes into picture. So our focus, if we are starting into design today, or if you have already focused on designing something, please have a wider vision of actually deploying it as a product itself. Meanwhile, all our publications, patents will anyhow definitely come along. It has to come. So the next question would be, how do I picturize my research into the product level itself? What are all the challenges which comes into picture? As simple as one of the MIMO antenna which we designed, we know that FR4 won't sustain it at that frequency. We know that. We easily go into Rogers substrates. So what basically happens in this? So these simulation tools have thermal analysis also. Yeah, I'm not only just doing high frequency analysis. We have a thermal analysis as in HFSS, ANSYS based ice pack. So wherein we can easily find out how much is the temperature affecting with respect to substrates also. That's also a basic study which I have to take care when if I am actually talking about physical layer design. So that's what majorly affects me in efficiency. Efficiency is not just about designing a standalone antenna and looking into how much is the radiation efficiency or how much is the incident power, accepted power to the radiated power. My life doesn't stop there. It's beyond that when I put my system on, put my component onto a system and what exactly happens. So these are all first things which I have to take care when I even talk about having my objectives or specifications to design. And then comes, yes, the first two antennas, omnidirectional direction, fine. And then comes what about the phased array? So how do I electronically steer these beams? Completely used, not just in aerospace and defense. Now it has to come. Now it has absolutely come into our commercial use also. So what is it that we are lagging or lacking, so that AI can help us to find out all these solutions? And this again a slide which basically says how important is antenna for me to in these modern networks. So if I have to handle high frequency propagation challenges, how well should my antenna design be? So the moment I talk about terahertz, what is the molecular absorption which is happening? So what kind of materials should I use as a substrate? Will the power handling capacity be same as the other ones? So these are all things which is something which I have to take care. And obviously, if I do not, I may end up having maybe to use higher energy consumption, which absolutely falls into thermal losses and degrade the user experience. So that is something which we have to take care. So coming to beamforming. So beamforming is, as the word itself says, I have to form a beam in a particular direction and nullify in the direction where I don't need, unless instead of broadcasting it in all directions. So what are all different types of beamforming we have? The beam has to now be formed in a direction where I am supposed it to be thrown. I know where the receiver is. If I'm considering myself as a transmitter, why would I put it in omnidirectional? I want the beam to be formed in this way itself. So if I have a complete array antenna, a phased array itself, so how well will I switch these antenna elements so that I can have a beam which is formed in the direction in which I want it to happen? Different ways. I have analog beamforming, wherein the phase shifts applied to signals at the hardware level itself. Right from probably we started with having a phase power dividers, and then we went into phase shifters, and then came about digital beamforming using absolute algorithms which can control multiple antenna elements in which would tell me the behavior of these phase gradients or wave fronts, which can steer the beam. And now we are talking about hybrid beamforming, wherein it combines both the analog and digital, gives me a better efficient performance. So why does it matter for me to have beamforming? So it improves my signal strength at the receiver. It also reduces interference. So that's also a major thing. Not just, for me, it's not only about having to throw the beam in the particular direction, it's also to nullify where I don't need it. So much more applicable for our defense applications. So it enables definitely more efficient energy use, obviously. And this is definitely essential when I'm talking about millimeter wave and terahertz, because higher the frequency, attenuation is more. I would be, since the signal losses are inevitable happening there, so, but still I need to survive at those frequencies. So beamforming is definitely essential. So how does this work? So as simple as, so we all know these point sources. If I consider an array of two elements, wherein as a simple example, if I have to say, I have stagnant water, wherein I throw stones. When I throw two stones at the same time, so we know that ripple occurs. So how does it occur? Where is it constructive and where is it destructive? So it's basically an example having a two element array wherein I am feeding it with same amplitude and same phase. So if I say same phase, I am throwing two stones at the same time. So when this is happening, so what is my logic? So ripples get deleted along the axis. So perpendicular to the where I am throwing, it gets added up. So this is basically my logic of broadside array, right? And if I throw the same stones at certain interval, assume one is at 0 degree, the other one is at 180 degree. So now I get the ripples which occurs in this water along the axis, and perpendicularly it gets nullified. It goes into destruction phase. So this gives me an end fire antenna. So basically what this says is, just by controlling the phase from 0 degree to 180 degree, I completely steered my beam from perpendicular to along the axis, broadside to end fire. So this is the simple concept of beamforming. Just by having a combination of specific amplitude and specific phase, I can have the beam to be steered in whichever direction I want, in the desired direction. And at the same time, I can have a destructive interference where I'm not supposed to throw the energy or unwanted direction. So in mathematical approach, if I have to go, I need to be careful with the vector summation and these adaptive algorithms, which help me in adjusting the phase shifts based on whatever feedback I get. So this database is now provided into the algorithms of artificial intelligence, which helps me in understanding many other things also. Just not an antenna throwing out energy and I steer the beam, but also looking into real-time scenario of if a building comes up, if I have base station deploy, another building comes up, and how do I mitigate this beamforming? If I have a moving vehicle, or if I am on mobility, what happens? How fast the switching happens? How the beamforming switches? So these things is something which comes in a picture. Challenges as such: complex environment with obstacles, reflections, and interference. This is something, so again, standalone antenna, one thing. If I have to consider the obstacles, reflections, and interference, that is also to be taken care when we are designing the antenna. So standalone, whatever we design, understand the beamforming, and then probably with the help of digital twin. So we usually have the complete urban scenario put with all high-rise buildings, trees, moving vehicles, and everything. And with these real-time, how do I understand the challenges in beamforming? And then comes user mobility. So we need to constantly recalibrate everything with respect to the beamforming also if I'm on a move. So that is one major challenge which comes. So how seamlessly it has to adapt itself. So then comes high frequency signals suffer with path loss and attenuation. Again, what do I do? So if I move into high frequency signal, my distance coverage is less. So the number of base stations which I have to deploy will get more. How do I do this? How do I take care of having a better base station capacity, having a good network network compatibility, and at the same time understanding the beamforming also? Thermal management, yes. And then comes what are all the different hardware limitations are there if I'm talking about a huge number of antenna array to be deployed. So here's where the need of AI comes, wherein if I have to recalibrate this mobility, so real-time adaptation and different type of predictive analysis and automatic optimization. So these things will help us overcome all the challenges which we will face in the beamforming when we get into the 6G challenges, 5G. So in this slide, what we see is, so wherever we are talking about beam selection or handover, or with respect to design or pre-coding or even the security, everywhere it's talking about deep learning. Reinforcement, yes. Regression, probably regression methods are very basic for me to understand in a very simple way. So if I have to go into the real challenges, we have to understand how exactly different deep learning and neural networks take care. And at the same time, SVM, the support vector machines, and all these algorithms would help us to understand how exactly the beam management could be done. Now we'll move into having known the importance of beamforming and what are all the different challenges which could occur with respect to moving into higher frequencies. So how exactly AI would help us, or AI would help in calibrating or understanding many things. So we know what artificial intelligence does. It takes the data, learns from it, understands the patterns, makes its own decisions. So in that we have many types. So one thing is supervised learning, wherein we have a set of data given, wherein few of it will take it to training, few of it will take it to testing, and few percentage of the complete data set, and it will learn. It's supervised, like how we teach in our classrooms. So unsupervised is given the task, you figure it out on your own. So it now finds the pattern. It doesn't have any labels to it. It finds different patterns. I don't know which is, if I'm talking in terms of antenna itself, so the labels would be what is the length and width of it, or S parameters, or the gain. So it will find the pattern on its own while learning on its own. Reinforced is something wherein we, like a trial and error basis kind. So it made some, it finds out an error, learns from it, and then goes into it. So reinforces something which probably we as a simulation engineer would have a very good example for us. When we design an antenna, we obviously, all of us here would definitely get into the simulation tool, right? How many times have we got the right result than getting wrong? I mean, all my experience, I'm actually very, very thankful that I have done so many mistakes. Don't we all think so? Doing that mistakes have actually given us a situation over the years that I know if this happens, this is what happens. I'm really grateful that I didn't get any results upfront in the first step itself. So trial and error is always a very good thing for us to start. So that is only the way for us to understand what kind of mistakes have we done. So in the next coming future, it would actually help us in a very, very, very huge way. Deep learning using all different neural networks for pattern recognition. So how do I relate these two antenna, the different AI algorithms is, analyzes the signal pattern. It will predict user movement and different channel variation also. So now I have to be very careful about the spectrum efficiency, how is the channel being utilized. And then comes, how do I optimize these beam directions and also take care of power allocation. So beam steering should happen seamlessly, and the power taken for these tasks should also be analyzed. So our EIRP and everything. So if we look into this slide, so AI right from a physical layer or MAC layer or network layer. So what is it that we are doing? If I have to do channel estimation and prediction, if we are talking about channel decoding, if we are talking about resource allocation and scheduling, everywhere AI will now put its hand. So 6G, as we know, 5G is also already getting into AI mode, but the moment 6G gets deployed, it's absolutely about AI assisted. Every different layer is AI assisted. Even for me to have a MIMO antenna or whatever designed with respect to space division multiple access, I need to be careful with, or I need to be knowing what kind of AI models do I need to predict or use to even find out the placing of these MIMO antenna for my mutual coupling. So that sensitive part, AI plays a different all the role. So what all can it handle? If I'm talking about beam steering, so it will help me in adjusting angles based on environment and user location. And then it will also help me in interference management. It's just not about beam steering. At the same time, it will also do the work of filtering unwanted signals. So, and then comes power allocation, reducing the energy consumption, at the same time maintaining the signal quality. And spectrum management. So how intelligently, if there is a surge of channels being used, how do I identify unused channels so that we have the complete connectivity always? And at the same time, the last one is a good one. We do know the lifetime of an hardware, but if I know that predicting the hardware as we use, I know every hardware what we buy has its own deadlines, has its own fault detection and everything. But the way we use it, otherwise, it depends due to many reasons, how we handle the system, how we do. So each one system now has the liberty to identify in their own way, the way we are using it to predict that this is how is happening, boss. You need to be careful how do you use it. So this you will lose. So obviously all our phones have our battery life predicting, right? So likewise, if AI can predict us the way we are using the hardware issues also, that will be a one more thing where we can take care of. So optimize, what are all algorithms which we can look into, and the algorithm which I am working on right now. So why do I basically need these optimization algorithms? It will predict me the best antenna configuration, so which helps me in having a complete throughput with minimizing the interference also. So coming to our genetic algorithm, so basically this works on our Darwin's theory of natural selection and everything, where only our the fittest individuals survive. So like that. So how do I? So it goes into different way of. I mean, genetic algorithm basically works on its way of initialization, and it does some work on fitness evaluation. It will select the best one, and it will iterate. So how do I use this in my antenna perspective? Is it will help me in optimizing the beam pattern to maximize my coverage while reducing the interference also, and it will also help me in finding out the best layout if I am talking about antenna array. I don't have to use it in the good old what we are using right now. So even the layout could be predicted by these genetic algorithms. So one of such algorithms which I am right now working on is the antenna layout for array using GAs. And power distribution also can be looked into it, but I am not sure how exactly we can look for these. And next comes is particle swarm. Again, the behavior of nature, wherein bird flocking and fish schooling. So here what basically happens is, if I have to optimize in a real-time communication, where the environment is changing frequently. So this is the best optimization algorithm which I have come across and read few articles. I have not worked on it actually. So, and this is quite simple to implement, and computationally it's quite efficient. Unlike genetic algorithm, this also doesn't need more derivatives or complex equations, and this is absolutely suited for dynamic environments. So that's one way for us to, if there is a real-time scenario wherein I have the environment which is frequently changing, so particle swarm is something which we can use. And coming to gradient descent, this is complete mathematical optimization method. So mostly works on minimizing errors between the predicted and the actual ones. So what this does is, I have I will define an error, or basically a cost function, and that needs to be minimized. So we use filtering techniques, H infinity or Kalman filtering, and compute the gradients and then adjust different parameters what I want to reduce these kind of errors. So this we will use this for fine tuning the phase shifts in beamforming. So this gradient descent is a wonderful algorithm wherein I have huge array system. Now, how does the sensitive switching happens when I'm talking about degrees? Certain very, very sensitive between few degrees itself. So how does this fine tuning happen, and how do I calibrate the power levels? So for those iterations or calibrations, we use gradient descent, and then coming to the reinforcement learning. So here it's about reinforcement, as we saw the different types of AI algorithms: supervised, unsupervised, and reinforced. It basically goes with trial and error. So here what happens is, this algorithm works on understanding the environment and learn from its feedback. So it just observes first, does some trial, understand from the behavior, and find out how it is happening. So now if I have a scenario of dynamic beamforming, real-time interference management, wherein I know that beamforming at one point it has to happen. What if at the same time I need to know how to block these unwanted signals? So that is when probably reinforcement algorithm learning would be used, which will help us to find out how exactly these beams should be adjusted so that I can block the unwanted signals also. So these algorithms, there would definitely be more to it. So these 4 is something which I have come across to understand the way I lay out my antenna arrays, the way I feed the, the way I do the phase shifting so that the beam steers efficiently. What if I have a dynamic environment which is changing frequently, and at the same time I need to mitigate my unwanted signals? So these 4 plays a very important role for these 4 challenges what I have. And then we talk about design factors. So what are all the design factors? So frequency band selection. So what is already known to us with respect to millimeter wave or 6G entering sub-terahertz. So, and what is the form factor? What is the different material I have to choose in order to have reduced losses? If I move into terahertz, will all the substrates what we are using so far, will it survive? Will it sustain? So that is something which we have to do as a groundwork. And how do we integrate this? So once select all these things, next comes is how do I integrate these with the other systems also, be it IoT or drones or smart factories or what. And at the same time, looking to environmental awareness, whether the terrains, the obstacles, and then comes how does AI enhanced design help me? Obviously, these will help me in understanding different shapes and layouts, and parametric sweeps find optimal antenna placement. Even in our simulation tool, we have these parametric sweeps. So I extensively use these optimetrics when I'm designing a system level. So a standalone antenna, yes, the moment I put it on the system on which I am supposed to design, too many things comes into picture. The dielectric constant of any number of materials will directly affect the system. So that is where I use optimetrics. So my easy way of understanding these are, if I have an antenna system, if I'm using it for body area network itself. So my textile antennas, whatever we design. So all the dielectric material, if I consider my skin, muscle, or whatever. So something is, the dielectric constant of all these is affecting my antenna. So my simple way of mitigating it, design a metamaterial which will nullify the effect of all these things. So we do have metamaterial absorbers, which is used for SAR reduction and everything. So simple example is how much is this dielectric constant of whatever inevitable things which is going to happen, even on a metal or on a body area network, which is the 2 things which I have worked over the years. So especially with these, when I have the phantom, in our simulation tools, we have homogeneous. We also have an option to inculcate heterogeneous also. Each one is having its own dielectric constants. So the moment I have these, how does antenna get affected due to this? It would definitely get affected. And second thing comes is, how do I nullify these effects? Somewhere we use quarter wave transformer and you nullify my reactance values, right? So same wise, if I use a metamaterial of certain design, which will give me a specific minus epsilon and minus mu, can I mitigate the dielectric constants of these otherwise, which is affecting my body? So that's how, that's where I use these parametric sweep. And if it is AI enhanced also, one of the algorithm which I am right now working on is with this, having a combination of antenna, having a combination of the complete heterogeneous phantom and metamaterials. So I'm feeding all different possible combinations of these 3 and telling the AI to come up with a particular best way to find out, which can give me an absolute antenna performance, which otherwise it is working standalone. Very good observation for us to even find out what is happening, how it is happening. So standalone happens. So the moment I integrate these things, how exactly can I do it? So these all, I haven't entered deep learning into in an efficient way. So that's where we probably communication engineer are not. I am lagging. All these years, putting my hands into only about looking into the antenna perspective of communication, how is that happens. The moment it's high time we enter into AI also. So the more we understand how in each and every way how these deep learning or machine learning help us in understanding many things, right from placement, right from the deployment of the system itself in a reliable way. Just a minute. So AI-driven beamforming in real time, if I have to see autonomous vehicles, so maintain connection during high-speed movements. This is one thing is autonomous vehicle. One major thing, what we are finding the lag is with respect to the blind spots. And at the same time, if it is high-speed movements, we do work on vehicle to vehicle, vehicle to infrastructure communications, right? So in that, if it is high speed also, how does your beamforming act? How with low latency and ultra reliable, how do I get adaptive beamforming? So this is where my beamforming will have to take the help of AI. Sorry. So now comes about spectrum sensing and allocation also. So what do we mean by spectrum sensing? So I have a complete RF spectrum, among which I have too many devices, too many services, and a number of networks. Right? So how do I monitor the available frequency band? So which are occupied and which are free. So this probably involves for me to have continuous scanning the radio environment, detect which of the signal strength is, I have a good signal strength, where exactly is the noise, which would lead me into interference. And also probably to identify which channels are currently in use, right, by other devices or network, so that I can use the unused channels. So these kind of predictions could actually be used by AI, which will tell me or predict which channels will be free and which can adjust allocations for better service. And at the same time, the moment the main thing comes is, how do I sense the spectrum? Only then I can go into allocation also, right? So that could be done by balancing the network traffic and having a good quality of service. So real time, when I look into it, especially emergency response networks, which are prioritized during disasters, by reallocating the bandwidth to those places. So this has to happen, I mean, dynamically, yes, but if it could be predicted. So there is something called as AI could now help us with predicting the channel availability. So for example, if I say a channel is typically congested during peak hours, so AI can now assign alternative channels to use before the congestion even occurs. So that's where probably the smartness falls in a picture. So adjusting allocation for service quality of service is fine. So if we have, again, if I look into real time, any disaster management, so obviously many users will attempt to access the network simultaneously, right? Which will lead into congestion and failures. So here, how does AI play its role in finding or reallocating this bandwidth, such as reallocating the emergency services as ambulance or police network? They should be given the priority to access these networks so that they know what is happening, where it is happening, so that they can reach there. Nothing should go wrong in these disaster management, definitely with network. So that is the smartness probably we have to look into this. So here, we talk about adaptive AI. So what is this? So artificial intelligence, different algorithms, how much can I take into it? So what is this adaptive algorithm? So now I'm talking about the intelligent systems altogether, which can monitor the network conditions and automatically adjust them to the changing environment. Either it could be traffic demands, either it could be signal variations. So it's basically like, unlike a static network, adaptive system learns and evolves over time. So it will provide us a optimal performance wherein I don't have to have human intervention at all. So it learns on its own. It's basically like self-organization. So these networks are called SONs, self-organizing networks. So what they take care of my traffic loads, they take care of my signal quality, the device types. So how many active users are there? Or what is the interference which is happening? Is there any noise? So what kind of device types are we using? Is there any weather or the environmental factor which is getting affected? So these adaptive algorithm will now reduce the need of manual tuning by engineers. So allow the network to respond in real-time scenarios. So how this happens is, it will analyze the past performance. So if a network experiences heavy traffic during weekdays or during peak hours, so AI can now predict similar load pattern for the future also. So we will be ready for accessing or looking into it and adjusting the way I have to allocate the bandwidth otherwise. So adaptive AI. So this advantages over reduced downtime. So reduced downtime, how would I say? So if a network faces any traffic surge or a hardware failure itself, so or if the base station is overloaded, assume. So traffic is automatically rerouted to the neighboring stations. So these all has to happen instantaneously and seamlessly. So if the signal strength drops in a particular area, so AI should now dynamically increase the power or modify my beam pattern to compensate these things. So each and every way where we are talking, everywhere there could be challenges which could occur, and there will be AI model coming into picture in each and every part of it. And coming to the application wise, where can I use it? It could be autonomous driving, it could be remote healthcare, it could be industrial automation. Everywhere adaptive AI can be diligently used in predicting interference patterns, reconfiguring the network patterns, and allocating the resources. So we talk a lot about edge computing. So what is this edge computing? So this is a way wherein we, in a simple way, when we are talking, it is basically a data which is processed quite closer to the user so that I have faster decision to take place. So if I'm talking about faster decision, reducing latency, so rather than having it being processed somewhere in the base station, if I can do it near the cloud servers or somewhere, so faster decision, and it will also help me in reduced load probably on different base stations. So AI applications on edge computing will probably help us in local channel optimizations, security also in how do I say, predicting potential threats also. So as simple as that. Applications of these, where could I use and all, I mean, right from indoor to outdoor applications. And if I'm talking about 5G, 6G networks, so these edge computing with adaptive AI will definitely help us in having ultra low latency, higher bandwidth obviously, and real-time response. This edge computing also helps us in having distributing processing task, allowing AI algorithm to make decisions faster. if I am talking about an unpredictable scenario and everything. And RIS is something with the whole country or everyone is talking about. Why do I need RIS? So the moment I move into high frequency communication of millimeter and everything, my attenuation, everything. So this is a simple scenario of having a reconfigurable intelligent surfaces, which can now steer the beam as a passive standalone element. It is intelligent, it's passive. I don't have to use a number of antennas to have the connectivity possible. So I can use a surface which can reflect, which can control the way it has to steer the beam by just adjusting the elements. So it could be metamaterial elements, it could be some control unit based devices, right from as simple as a varactor diode or FPGA control. So AI roles here is dynamically controlling reflection angles and also optimizing signal paths in real time. So we talk about these RIS for having these dynamically controlling reflection angles, so which will obviously improve my coverage even in an indoor, reduce the interference. So RIS would not only help me in steering the beam into the direction where I want, in different directions, it would also help me in reducing the interference and obviously the cost-effective solutions. So probably goes with designing metamaterial, appending my control unit for dynamically steering depending upon which of the unit cell should be on or off, so that I have a wavefront in a certain direction for my beam forming to happen in these direction or steering it. Then comes what is the AI roles in 6G communication. So the moment I move into terahertz communication, I will definitely have a liberty of ultra high speed data transfer, but it would also help have challenges in molecular absorption. And with considering these, AI can be useful in predicting channel estimation, having adaptive filtering, beam forming. So now it is inevitable for us to move to high frequency. So at the same time, if I can understand different challenges which is happening, as in if we are talking about 0.1 terahertz, sub-terahertz communication, or there is high path loss, there is atmospheric absorption like molecules of water vapor, oxygen, which completely absorb my terahertz signal, and there will be scattering. Physical objects can completely disperse the signal itself. So with these, how do we have adaptive algorithm and beam forming and energy management so that the AI could be efficiently used? So application-based AI in 6G terahertz, we can think about holographic displays. So seamless, very high resolution data streaming without any delays. Or we can talk about, even if it is for space communication, high bandwidth link between satellites and ground. Medical imaging, we can use it for having fast and high fidelity data transfer for our remote healthcare systems and it. And what is the security and privacy that needs to be taken care of? We have regulatory framework from GDPR, that is General Data Protection Regulation. Yeah, this is a European data protection law, which basically governs about how much personal data could be put out for our privacy. So when these things comes into my security issues or privacy issues, right to access and erase data. So this is where the user will also be benefited. If my data is being seen in the communication, how will AI now be taking care of having the protection for the communication what I am doing? So it could be in terms of the different telecoms standards, what we have, 3GPP, ITU, IEEE standards and everything. How does AI has its role is real time having the security standards to ensure that we do not have any backdoors in our critical communication infrastructures and all. Ethical AI guidelines basically talks about accountability, security, human oversights, um, which is again essential, right? We not only talk about having this AI in terms of channel modeling, but also in terms of ethical guidelines, which will safeguard our information also. And then what all I need to be looking into when I'm designing is different sensors, all the processors, data pipelines, and different AI models. So protocols, what we have to take care, which are compatible with my 5G and future 6G framework. So we can work on different open AI platforms. So how do we go about it? I mean, in a simple way, I work on the structure, the antenna modeling itself, whichever tool we are comfortable, and then use these data sets to train the AI algorithm. So basically, when I am working on it, 80% of my data set goes into training, and the 20% we leave it to testing. So it's a standard way of executing it, and then validating it with the hardware and the loop systems. So one such RIA system, what we are developing right now, is about this, designing the system standalone, and then looking into certain AI models which can help me route different prediction and control unit for my beam steering. So best practices, combine simulations with real world trials. So always better to do this in the simulation. So now these simulation tools are so powerful that we can understand, or we can get results for many real time. So if I'm talking about RCS or bistatic, everything. So I can analyze so many things rather than designing it a standalone system actually. So where can I use it? Not restricted to what we see on the screen here. Could be used for smart cities, autonomous vehicles. So beam forming, one thing which we are planning to work on is deploying RIS on drones itself. So good old days, I mean, I don't know, I have not done these communications. We had duct propagation long back. So why don't we use the same here with respect to drone communication also? Why don't I use my RIS on drones, which will help me to have these beam steering or beam forming happen? Otherwise, when I have mobility, not just in an indoor or a standalone system which is being deployed in an outdoor as an RIS, what can I do if it is moving also? So it opens up opportunities in a many way for us to think what could be done, what can be done. So drone technology, something is going in a huge way. So how can I integrate my kind of interest, my kind of work into that, so that I still can think about our system development as a whole, not just as a component level. Yeah. So future trends. So self-learning antennas. Fortunately, the shape and different ways of antennas have not stopped. So we, as a antenna engineer, are still surviving. But then again, if AI can take over the complete, one of the CNN model which we recently did, we actually trained all kind of antenna shapes. And it beautifully gave me, if I want high gain, what is the shape? If I want wideband, what is the shape? If I want multi-band, what is the shape? So somewhere antenna is learning itself. So how do we now intelligently go hand in hand with it? And next, again, a lot of noise is happening with respect to quantum communication or quantum assisted communication. So how can beamforming, terahertz, help us in quantum communication? I mean, I won't be able to tell more about it. The only thing is, the moment we enter 6G, AI is absolutely there. If I have to talk about QKD and everything, or probably non-line of sight communication in terahertz, that probably directly falls into my quantum communication. How do I now intelligently take care of these things? And then at the same time, ethical AI frameworks. So overall, today we just discussed about what are all the different challenges which can occur and how is the impact of this AI directly into our real-time understanding and deployment. So it's high time we inculcate the power of AI into our physical layer also, no matter what we are designing here. So since we are restricting our discussion into antennas and different beamforming techniques, how different algorithms will help me not just in the physical layer, not just in the understanding different control unit, but also in channel estimation. So probably we now have understood or gotten a glimpse of, okay, this is how it needs to be treated. We need to go hand in hand with respect to adaptive AI and edge computing also, which will help us in 6G and definitely, yes, when we move into quantum communication also. So here I end my talk. And anything to discuss, please feel free to have a discussion. I am also in the research mode of integrating AI into my subsystems. So anything which we want to discuss now?
Any queries from the participant side? Any queries?
Hello, ma'am. Hello.
So sorry, sir, I think I...
Hello, ma'am.
Yeah, am I audible, sir?
Yes, ma'am. Actually, I want to know the how is there any process to how much data is required for the optimization. Suppose we are using a CST software for metamaterial, then how much data will be required for the
As much as possible, sir.
but is there any rule and
no,
how much
sir,
data?
if you keep a minimum data, like if I take, if we are simulating in our software,
Yes, sir.
we take the how do I say, if it is a linear count, we usually take 400 points or 101 points or 1000 points.
Yes,
So
ma'am.
my complete band, if I'm simulating from 1 to 3 gigahertz,
Yes, ma'am.
so I will have one data there. So it will take more time for simulation. But if I have more data here, so if I plot my S parameters and I can import my CSV file. So
Yes,
this becomes a complete data set for our analysis in the prediction.
Yes, ma'am.
Yeah, so we can start with, probably I started with 400 data sets, sir.
400 data sets.
Yeah,
And
I mean 400 points if we give in the frequency band, what we take linear count interval, I think that would be enough.
okay.
And next comes is what kind of algorithms we use. We started with linear regression, as simple as linear regression, which
Yes,
goes
ma'am.
as a straight line equation, which,
Yes, ma'am.
which didn't work for us because my S parameter prediction is
Yes,
different.
ma'am.
Then we moved to polynomial regression. Then we moved to decision tree, and now we are somewhere entering into CNN.
Okay, okay. Actually, we are taking approx 50,000 data. Is it sufficient or not?
Absolutely sufficient, sir. So your hardware also should be strong enough now.
Yes, ma'am. Yes, ma'am. Thank you, ma'am.
Sure, sir.
Hello.
Yes, sir. Please, sir.
Good evening, ma'am.
Good evening.
Ma'am, from where? Actually, I am very new to this AI and ML field. Actually just a basic question that how can we design a simple microstrip patch antenna using an AI? Let's suppose that I want to build a microstrip patch antenna for ultra wideband range. Then how to proceed? Just a simple.
Okay. So I initially have to feed in the so AI basically works with, so usually what we do, if I have addition to be done, I I know that I have to do 2 plus 4. I give the rule.
Okay.
In AI, what happens is I give the input and the output.
Input and output. Okay.
So I tell the algorithm that my input is so ultra wideband. We somehow know that we will use all the parameter I need is radius of that circular structure what I use.
Okay.
So generally, if I want resonant antenna, I go with rectangular or square structures. If I
Okay.
want wideband, I go with a circular structure. Or
Okay.
elliptical. So if I give the input that play with different values of radius at certain frequency, and we assign that the basic relation of wavelength to frequency. So I just have to prompt it that you consider these things. I don't have to give the equations also. AI will pull out the information how it needs. So if I give the input and then if I give the output that I want the coverage or S parameters having -20 dB for a range of 1 to 5 gigahertz.
Okay.
So now I need to give it certain data set. So this data set will be the first iteration what I do in my simulation too.
What kind of data I need, and where is it available?
You are using any simulation tool, sir?
I am using CST and HFSS.
So you would have designed a wideband antenna?
Yeah, I have designed it.
Okay. So you have S parameters results?
Yes, S11 and S21.
Yes. You can import the CSV file?
Yeah, definitely.
That is the input to your algorithm.
Okay, that CSV file will be the input data, and that will be given to the algorithm.
Yes.
And then I will ask that question that now I want to design it for 10 gigahertz.
Yes.
So and then it will give.
Adapt itself. Yes.
Okay. Good. Thank you.
You can, okay. I mean, I have my algorithms in my workstation.
Okay, actually, ma'am, when I have read the paper related to AI and ML regarding the antenna designing, most of the papers are not having that code. Then actually I don't know how to proceed for that. Is there any video or any link you are having so that I can be benefited?
Sir, I can share you the code which I have written.
Okay.
Mohit sir, maybe I will share it with you. You can share
Yes, sir. Yes, madam. I will.
So I will attach the CSV file also which I used for my design.
Okay.
I will share the decision tree algorithm which I had used to predict the kind of antenna which I wanted, and how exactly the simulation predicted, and how exactly my algorithm predicted much better than what simulation tool gave.
Great, ma'am. It will be. Thank you.
Maybe that would be a start for us to have our AI journey also hand in hand with our design.
Yes, ma'am. Certainly. Thank you, ma'am.
Sure. Thank you.
Can I ask two questions regarding this? Is it my voice is audible?
Yes, please tell me.
Ma'am, first thing that you are designing the antenna for military application. In the video, I heard that. At the time when I designed the antenna, always I think that everyone told about the Rogers substrate material, fast flow substrate material. But at the time, my guide told me that you have to design this antenna with the help of glass PTFE, and that material is applicable only in the military side, which will be not available for all students because for some kind of radiation that will affect to the military. So at that time my guide told me that it's that material which gives much more thickness. So
sorry.
It is best applicable in spite of all the substrate material. It is good for better communication, for better gain and better directivity. And always the return loss must be less. So why researcher and or student are not using this material?
Sir, the main thing is, see, 6 years back,
I know that this is costlier. Not applicable for all.
That's the only reason. How can unless we have funding, me also, when I was in academics, I really faced these challenges wherein for us to procure those material was a challenge.
And
That is yeah.
second question is that, ma'am, actually, is there is any correlation thing that I designed my microstrip patch antenna on HFSN and CST, and is there anything, any software or any waveguide or any wiring connection that I have to connect this to my data set or to the AI tool? So can we go for designing the antenna with the help of AI, and shows that my antenna work with the some kind of relations to AI?
Yes, I know about ANSYS tool. We have Pi. What do we have? Python integrated to it. I forgot the name about it. Pi AEDT or something, I think. So you can design the tool, design your from in this HFSS, whatever 3D structure you design, and there's Pi AEDT, which you can be integrated. You can convert the complete design into a code and import it into your Python code, which is again integrated in the HFSS itself. And we can
Means that after designing of antenna, you can implement this antenna design, and automatically it will convert with the help of AI tool, and they will configure the data set also.
Yes, this happens when the simulation tool has an integrated Python with it, the AI models with it. So if you want to do it otherwise, you have to give the input to these AI algorithms. Like as in I fed, for me to understand a better prediction of S parameters, I use decision tree algorithm. I took the CSV file. So for CNN, what we did is we took around 1,000 designs of antennas. CNN basically works on images. So all different shapes were given as an input to predict now what kind of antenna shapes can I use for what kind of applications.
Fine, ma'am. Thanks.
Any other queries?
Hello, ma'am.
Yes, sir.
Suppose we have designed any MIMO antenna. Okay. Suppose isolation is less. Suppose -10 dB. If we want to increase the isolation approx -20 dB, then how will you by using machine learning?
Okay. So this again needs a lot of data sets. So you may have to have your data set from your mutual coupling or what losses S21 what you take, and we will have to feed it into the algorithm to say that which of the values are best for it.
Yes, ma'am.
So then it will redesign the spacing or the shape or the size in such a way then tell you that if you want this kind of output, what could be the spacing between. Mostly for me, the coupling probably matters with how I space it.
Yes.
That could be the reason, sir. Yeah. So or whatever may be the query, my only input to AI is what kind of input and what kind of output I'm expecting. It will generate me the complete rule itself. It will tell me this is how you need to place to get this.
Okay, ma'am. We have to some target.
We basically mean have good data sets.
Okay, ma'am. Thank you.
Any other queries?
For the antenna data set, I will share the code and the CSV files, sir, by end of this, after this meeting.
Any other queries from the participants? Thank you, madam.
Yes, sir. Thank you so much, sir. Thank you so much for this opportunity.
On the behalf of the participants, organizing committee, and from MIT Group of Institutes, I extend my heartfelt gratitude to Dr. Shweta Amit, madam, to give her valuable time to this FDP. Madam has very well explained AI integrated antenna, its application, and I want to thank you, madam, that she is sharing also the data set and code to the participants. That's very valuable to them for learning.
Sir, you have to start somewhere, sir. If someone help me, and it will go on like that.
Thank you, madam.
Ma'am, I have one question. Ma'am, I have one question.
Yes.
Ma'am, nowadays in antenna, number of researchers are switching to the deep learning. What is the main difference between machine learning and deep learning in the above antenna?
Sir, AI is for big picture. Machine learning can happen in a surface level. So deep learning is a subset of my machine learning, wherein I need lots of data, too much data to give accurate results.
We have to require the much data.
Lots of data, too many data sets to get into deep learning, because it will definitely give me accurate results.
Okay. Thank you, ma'am.
So all neural network based. CNN. It starts with CNN.
Okay. What will be the main difference between code in ML and deep learning? Is there any difference in coding?
Yeah, coding. No, sir. I mean, the programming what I have written, the data is the same. In deep machine learning, I simply use data sets. The CSV file is enough. The moment I move into CNN, especially, I only have worked with CNN so far, so it needs the images. And when I started with 10 images, the prediction was very bad. So we wanted it. Basically means if I have 1,000 data set, it's good for me to do machine learning. If I have 10,000 data set, deep learning is good. The more the data, more will be my way of predicting things much precisely.
Okay, ma'am. Thank you so much for nice presentation.
Thank you.
Good evening, ma'am. Good evening, ma'am.
Good evening. Please tell me.
Ma'am, last question. Is there any possibility to design or else equivalent circuit using AI?
Design what? Sorry?
For RLC equivalent circuit for our proposed antenna.
Okay.
Using AI?
Let me think. I have not come across this. If assume I design my circuit in HFSS, not in HFSS 3D, in my circuit.
Okay.
Okay.
Because many researchers are expecting to validate our
circuit, much needed everywhere. So I am just thinking what could be done. So generally what I do is, if I am designing a complicated antenna and placing it on, usually I work on wearable. So it's when I'm placing it here, my complete impedance matching gets knocked out. So what I do is I push this HFSS design into circuit. In HFSS we have circuit also, no? So I take my design into circuit and I put my S parameters in Smith tool. In HFSS there's Smith tool also, which will give me a compensatory circuit, which will compensate with my quarter wave transformer, and I'll get 50 ohms for my antenna. This is something which
yeah, ma'am. Possibilities are there, but many researchers confusing on researchers.
I'm thinking if I can get these S parameters data set somehow, which is now giving me a circuit altogether, right?
Yes.
Compensatory circuit. So if I can somehow get the data set from that and put it in my algorithm, which can predict different circuit level. This is a good question, ma'am. Let me work on it.
Okay,
Give me a month's time. I will
if you get the answer, please share us, ma'am.
Definitely. I will put my email ID. Any doubts?
Sure, yeah.
I mean, it's learning for me also. So it's always good.
Yes. Thank you, ma'am. Thank you. I will mail you.
Definitely.
Any other queries from the participant side? I think its queries are over, madam. Thank you, madam, for your valuable time again.
Sure, sir. Thank you, sir. Sir, can I please have a pic, if you don't mind, if anyone can turn off their cameras?
Okay, madam, wait. I will allow them to turn on. Participants can turn on their video. Madam, want to take one screenshot? All the participants are requested to turn on their video.
Just yes. Thank you. Thank you so much, sir. Thank you, everyone. Thanks a lot.
Thank you, ma'am. Thank you.
Sure.
Thank you,
Have a
ma'am.
nice day. Have a nice weekend. All the best. And anything mutual
Ma'am, thank you
learning,
so much.
I have put my
Thank you
email
so much,
ID.
sir.
We always learn together and grow together.
Thank you, madam. Thank you very much.
Sure, sir. Thanks a lot.
Thank you so much, sir.